Black holes are mostly described as giant space vacuums or invisible monsters hiding in the universe. But what if what you know only touches the surface? Behind the simple explanations is a strange world where gravity can slow down time, where the laws of reality bend and even break, and where the universe hides some of its most shocking secrets. In this video, we'll explore the incredible truths about black holes, mysteries so strange and unbelievable that they could change how you see space, time, and even life itself. Before we start, tell us in the comments where in the world you're watching from and what time it is right now. Then sit back and join us on this journey to discover the most mysterious objects in the cosmos. A black hole is one of the most extraordinary and mysterious objects in the universe. Imagine something so massive and so tightly squeezed into a tiny region of space that its pull of gravity becomes unstoppable. Nothing, not even the fastest thing we know, light itself, can escape once it gets too close. It is like a cosmic trapdoor, a place where escape becomes impossible. The brilliant scientist Albert Einstein, through his famous theory of general relativity, showed that if a very large amount of mass is crushed into a very small volume, it would create a strange and powerful object unlike anything else. That is what we now call a black hole. Around every black hole lies an invisible boundary called the event horizon, often described as the point of no return. If anything crosses this line, whether it is a planet, a star, or even a beam of light, it is forever lost to the black hole's grasp. Strangely enough, black holes do not have visible features right at this boundary, yet they completely change the fate of anything that dares to cross it. Physicists also compare black holes to something known as a black body, which is a perfect absorber of light. Nothing bounces back, everything disappears inside, making it appear absolutely dark. But quantum physics tells us there is a twist. Black holes can give off a tiny glow of energy known as Hawking radiation. This is like a faint warmth that leaks out. But for normal black holes formed from stars, this effect is so incredibly weak that it is nearly impossible to detect with our instruments. The story of black holes began long before Einstein. In the 18th century, two scientists, John Michel from England and Pierre-Simon Laplace from France, imagined the possibility of dark stars. In the year 1784, Michel wrote a letter suggesting that if a star were as dense as our Sun but about 500 times bigger, its gravity would be so strong that even light could not escape. He even predicted that such hidden stars might reveal themselves by tugging on nearby visible stars. Just over a decade later, in 1796, Laplace also wrote about the same idea, providing detailed calculations. For a while, the idea of these invisible giants fascinated scientists, but by the early 19th century, interest faded. This was because scientists had discovered that light behaves like a wave, not just like a particle, and they were unsure if gravity could trap a wave. The concept of dark stars slipped into obscurity, until Albert Einstein revived the idea in a new way. In the year 1915, Einstein's general theory of relativity showed that gravity bends the path of light itself. Just a year later, in 1916, Karl Schwarzschild, working with Einstein's equations, gave the first exact mathematical description of what the gravitational field of an extremely dense object would look like. Another physicist, Johannes Droste, independently reached the same result. This description revealed a strange mathematical distance now known as the Schwarzschild radius, the point where gravity becomes so extreme that escape is impossible. At first, this looked like a troubling mathematical glitch, but later, in 1924, Arthur Eddington explained that the infinity problem was just a quirk of the equations. In 1933, Georges Lemaitre showed that this radius was not a physical flaw, but rather a coordinate effect, meaning it was a feature of the math, not a real-world error. Eddington himself wondered what would happen if a star collapsed all the way down to this Schwarzschild radius. In a book published in 1926, he described how light from such a star would behave as if it were falling stones, never escaping, and how the surrounding space would curve so severely that it would close in around the star, hiding it from the universe. For many years, black holes remained only as fascinating possibilities on paper. But in the 1960s, astronomers realized that these strange objects were not just theoretical. They were real, and could form naturally when giant stars reach the end of their lives. The first strong evidence came in the year 1971, when researchers discovered a powerful X-ray source in the sky named Cygnus X1. This turned out to be the very first recognized black hole. Black holes are usually born when massive stars collapse under the weight of their own gravity. Once created, they do not stop growing. They can feed on gas, dust, and even entire stars that stray too close. Some black holes are unbelievably huge, millions of times the mass of our Sun, and these monstrous versions, called supermassive black holes, sit quietly at the centers of galaxies, including our own Milky Way. Even though black holes themselves cannot be seen directly, astronomers detect them by watching how they affect the world around them. Gas and dust spiraling inward form a bright, hot whirlpool of matter called an accretion disk. This glowing ring can shine across the universe, sometimes becoming a blazing beacon known as a quasar, one of the brightest objects ever observed. Occasionally, a star drifts too close to a supermassive black hole, only to be torn apart, stretched into glowing streams of gas before disappearing forever. By tracking the dance of stars around these invisible monsters, astronomers have confirmed the presence of black holes and even measured their mass. Using this method, they discovered that the powerful radio source called Sagittarius A, at the center of our galaxy, hides a black hole weighing about 4,300,000 times the mass of the Sun. Back in the year 1931, the young Indian-American scientist Subrahmanyan Chandrasekhar studied extremely dense stars, now known as white dwarfs. Using ideas from relativity, he showed that if such a star became heavier than about 1.4 times the mass of our Sun, it could not stay stable. This limit is now called the Chandrasekhar limit. Beyond it, the star must collapse further. Many great scientists of his time, such as Arthur Eddington and Lev Landau, resisted his conclusion, believing some unknown force must stop the collapse. In reality, stars just a little heavier than this limit shrink even further to become neutron stars, which themselves are unimaginably dense. But if the star is heavier still, there is no escape, and the collapse continues until a black hole is born. Then, in the year 1939, two important physicists, Robert Oppenheimer and George Volkoff, took this idea further. They suggested that neutron stars also have a limit, now known as the Tolman-Oppenheimer-Volkoff limit. If a neutron star becomes too heavy, heavier than this limit, it will collapse even more. They believed that nothing in physics could stop this collapse, meaning some stars would eventually become what we now call black holes. Their early calculations, based on the Pauli exclusion rule, a rule in quantum physics about how particles act, gave this limit as about 0.7 times the Sun's mass. Later, after thinking about the pushback forces between neutrons themselves, this estimate was raised to somewhere between 1.5 and 3 times the Sun's mass. Even more recently, after astronomers saw a neutron star crash called GW 170817, which is thought to have formed a black hole soon afterward, scientists adjusted this limit to about 2.17 times the mass of the Sun. Oppenheimer and his colleagues also studied the strange nature of what happens at the edge of a black hole, a border called the Schwarzschild radius. They described this border as a place where time itself seems to stop, at least from the view of someone watching from far away. This led them to call these collapsed stars frozen stars, because an outside watcher would see the surface of the star look frozen in time, just as it reached this strange edge. Interestingly, also in 1939, Albert Einstein tried to prove that black holes could not exist at all. In a paper called On a Stationary System with Spherical Symmetry, consisting of many gravitating masses, Einstein used his own theory of general relativity to argue against black holes. But only a few months later, Oppenheimer and his student Hartland Snyder published another important paper called On Continued Gravitational Contraction. Using Einstein's theory themselves, they showed how black holes could actually form under certain conditions, marking the first clear forecast of black holes in modern physics. Fast forward to the year 1958, when David Finkelstein gave a new and clearer meaning of the Schwarzschild radius. He explained it as an event horizon, which acts like a one-way wall. Things can fall in, but nothing can come back out. Finkelstein also developed a new way to look at black holes that included the view of someone falling into one, not just an outside watcher. Around the same time, mathematician Martin Kruskal had found a similar idea, but it wasn't fully valued until later. Over time, the shared work of Finkelstein and Kruskal led to the creation of special coordinates, called the Kruskal-Sekaran coordinates, which help physicists understand black holes from many viewpoints. The time from the mid-1960s to the mid-1970s is often called the golden age of black hole research. During these years, the study of black holes and Einstein's theory of general relativity became a main and popular field of study. During this exciting time, scientists found more general and realistic answers to describe black holes. In 1963, Roy Kerr found the exact math description of a spinning black hole. Just 2 years later, in 1965, Ezra Newman found the answer for a black hole that is both spinning and electrically charged. Further work by Werner Israel, Brandon Carter, and David Robinson led to what is known as the no-hair rule. This rule says that a stable black hole can be fully described by only 3 features: its mass, how fast it spins, called angular momentum, and its electric charge. At first, some physicists thought that the strange parts of black holes, especially the singularities where densities become endless, were just math quirks caused by the special setups used in the models. In particular, scientists like Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz tried to show that these singularities wouldn't appear in more realistic cases. But by the late 1960s, Roger Penrose and Stephen Hawking used strong math methods to prove that singularities do usually appear in gravitational collapse. This was a big breakthrough. Penrose was later given half of the Nobel Prize in Physics in 2020 for this work, although Hawking had died in 2018 and could not receive the prize. Astronomy also made amazing findings during this golden age. In 1967, Anthony Hewish and Jocelyn Bell Burnell found pulsars, stars that send out steady beats of radio waves. By 1969, these pulsars were known to be quickly spinning neutron stars. Before this finding, neutron stars and black holes were mostly theory, but now astronomers knew they were real objects in space. This discovery sparked much greater interest in all kinds of superdense stars formed by gravitational collapse. In the early 1970s, astronomers studying a bright X-ray source in the constellation Cygnus, called Cygnus X1, and found in 1964, gathered enough proof to decide that it was the first widely accepted black hole candidate in our galaxy. Around the same time, important theory work was done by James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking that led to the building of black hole thermodynamics. This set of rules shows how black holes act in ways similar to everyday objects with heat and energy. For example, the black hole's mass is linked to its energy, the surface area of its event horizon links to entropy, a measure of disorder, and the surface gravity links to temperature. Then, in 1974, Hawking showed a truly amazing result using quantum theory. Black holes are not fully black. Instead, they give off radiation, now called Hawking radiation, as if they were warm objects with a temperature linked to their gravity at the surface. More recently, on the 11th of February 2016, the LIGO and Virgo science teams announced the first ever direct detection of gravitational waves, ripples in spacetime caused by 2 black holes joining together. This was a huge event in astrophysics. A few years later, on the 10th of April 2019, scientists shared the first direct picture of a black hole and its surroundings. This picture came from the Event Horizon Telescope, which looked at the supermassive black hole at the centre of the galaxy, Messier 87, back in 2017. Also, the Gaia space mission has found signs of stars moving around black holes much closer to us. One such black hole, named Gaia BH1, about 1,560 light-years away, has a sun-like star moving around it. Another black hole, Gaia BH2, seems to have a small, cool brown dwarf star in orbit. Even though astronomers have only found a few dozen black holes in our Milky Way galaxy so far, scientists guess there are hundreds of millions out there. Most of these black holes are alone and don't give off any radiation, so they are very hard to spot. They can usually only be found by the way their gravity bends light around them, a happening called gravitational lensing. Back in December of 1967, during a talk given by the famous physicist John Wheeler, it is said that one of his students suggested the phrase black hole to describe these strange cosmic objects. Wheeler liked the term because it was short, catchy, and easy to remember. In other words, it had great advertising value. Because Wheeler was a leading figure in physics, the name quickly became popular, and many people credit him with making the phrase. However, the story is a bit more complicated than that. Other scientists were already using the term black hole around the same time. A science writer named Marcia Bartusiak traced the phrase back to the early 1960s, when physicist Robert H. Dicke reportedly compared these strange objects to the Black Hole of Calcutta, a notorious prison in India where people went in but never came out alive. This dark picture fit perfectly with what these cosmic black holes meant. The phrase showed up in print as early as 1963 in magazines like Life and Science News. It was also used by science journalist Anne Ewing in an article called Black Holes in Space, published on the 18th of January 1964. This article covered a science meeting held by the American Association for the Advancement of Science in Cleveland, Ohio. Now, what exactly is a black hole? One of their most mind-twisting features is that the speed needed to escape their pull, called the escape speed, is faster than the speed of light. Because nothing can move faster than light, not even light itself can escape from a black hole once it crosses a certain border known as the event horizon. Scientists have built something called the no-hair rule to describe what a black hole is like once it settles down after it forms. According to this idea, a black hole can be fully described by just three simple physical features: its mass, how much stuff it has, its electric charge, whether it has a positive or negative charge, and its spin, how fast it is spinning. Apart from these three features, black holes are thought to be fully plane, meaning that any two black holes with the same mass, charge and spin would be impossible to tell apart. This idea is very special because these three features can be seen and measured from outside the black hole. For example, a black hole with an electric charge will push away other objects with the same charge, just like any charged object would. In the same way, the total mass of a black hole can be measured from far away using methods like those used in gravity studies on Earth. Its spin can also be measured from a distance by watching how it twists space and time around it, an effect called frame dragging. When something falls into a black hole, any detailed information about its shape or the way its electric charge is spread out disappears to someone outside. Instead, this information is spread evenly along the black hole's edge, which acts like a kind of stretchy, sticky skin with drag and electrical resistance. Scientists call this the membrane idea. This is very different from other forces, like electromagnetism, which can be reversed perfectly and do not have drag on a very small level. Because black holes eventually settle into this simple state defined by only three features, all other detailed information about what fell in is lost to the outside world. This includes important quantum information, like certain saved numbers related to particles. This strange loss of information is called the black hole information puzzle, and it is still one of the biggest mysteries in today's physics. The simplest kind of black hole is called a Schwarzschild black hole, named after the German scientist Karl Schwarzschild, who found the solution in the year 1916. These black holes have mass but no electric charge or spin. According to a rule called Birkhoff's rule, the gravity you feel far away from such a black hole is exactly the same as if all that mass were packed into a normal round object, like a planet or star of the same size. So the common idea that black holes pull everything in from far away is only true very close to the black hole near its event horizon. There are other, more complicated black holes too. If a black hole does not spin but has an electric charge, it is explained by what's called the Reissner-Nordström model. If it spins but has no charge, it follows the Kerr model. The most general known kind of still black hole has both charge and spin, explained by the Kerr-Newman model. Although a black hole's mass can be any positive amount, its charge and spin are limited by the size of its mass. Black holes with the smallest mass allowed for a given charge and spin are called extremal black holes. There are possible answers to Einstein's equations where this limit is broken, but they do not have an event horizon, and instead show something called a naked singularity, a point of endless density that can be seen from the outside. These naked singularities are thought to be unreal, and a rule called the cosmic cover-up idea says that they cannot form when real stars collapse. Computer tests support this idea. Because the electromagnetic force is so strong, black holes formed from collapsing stars are expected to be almost without charge, carrying nearly the same charge as the star they came from. But spinning, or turning, is expected to be very common among black holes, just as it is for many other objects in space. For example, a well-known black hole candidate called GRS 1915 + 105 is believed to spin close to the fastest rate allowed by physics. Scientists often sort black holes by their mass, no matter how fast they spin. The size of a black hole, measured by the radius of its event horizon, called the Schwarzschild radius, grows directly in step with its mass. The most striking feature of a black hole is the event horizon. This is not a solid surface like the crust of a planet, but instead an unseen boundary in the fabric of space and time. Once matter or light crosses this boundary, there is only one way to go: inward, toward the crushing mass at the black hole's heart. No signal, no object, not even a beam of light, the fastest thing in the universe, can make it back out once it has gone past this point. The event horizon gets its name because any event that happens inside it is forever hidden from the outside universe. No information, no image, no sound of what happened inside can reach an observer on the outside. From their view, it is as if that event never happened at all. Albert Einstein's general theory of relativity tells us that mass bends the very fabric of space and time around it. The bigger the mass, the more strongly it bends this cosmic fabric, forcing the paths of particles and even light to curve toward it. In the case of a black hole, the bending is so extreme at the event horizon that there are no possible paths that lead away from it. Now here is where things get even stranger. If a distant observer were to watch a clock near a black hole, they would see that it seems to tick more and more slowly compared to clocks farther away. This effect, called gravitational time stretching, would make it look as though an object falling toward the event horizon slows down endlessly, taking an endless amount of time to actually reach it. From the outside, every process on the falling object seems to slow greatly. Its movements, its chemical reactions, even its heartbeat if it were alive. The light it gives off would grow more and more red and dim, an effect known as gravitational redshift, until it disappears fully from sight. In truth, this fading happens very quickly, often in less than 1 second, though the picture of slowing forever remains for the outside observer. Strangely, if we imagine an unbreakable astronaut falling into a black hole, they would notice none of this. To them, their watch would tick normally, and they would pass the event horizon in a normal amount of time without any cosmic drama. This is because, according to Einstein's sameness idea, nothing about the local physics would tell them they had crossed the horizon. When a black hole is still and not spinning, its event horizon is shaped like a perfect ball. If the black hole spins, the event horizon flattens a little at the poles, taking on a squashed shape. At the very core of a simple, non-spinning black hole, the kind explained by the Schwarzschild model, lies the gravitational singularity. This is a place where the bending of space and time becomes endless, and the known rules of physics break down fully. For a non-spinning black hole, this singularity is a single point with zero size but holding all of the black hole's mass, giving it endless density. For a spinning black hole, the singularity is stretched into a thin ring that lies in the flat plane of the black hole's spin. Once anything crosses the event horizon of a Schwarzschild black hole, there is no turning back. It will surely reach the singularity. The doomed traveller could fire rockets to slow the fall, but this would only delay the end, not stop it. Before reaching the singularity, the object would be torn apart by tidal forces so strong that they stretch it lengthwise and crush it sideways, in a frightening process called spaghettification, or the noodle effect. Black holes that spin, Kerr black holes, or carry an electric charge, Reissner-Nordström black holes, give even stranger possibilities. In theory, it might be possible for something falling into such a black hole to avoid the singularity altogether. The math of these answers suggests that the black hole could connect to another region of space and time, forming a kind of wormhole, a tunnel that could, in idea, lead to another universe. But these ideas remain purely in theory, because even the smallest shake would likely destroy such a path. Some answers also suggest that in a spinning black hole, it might be possible to travel along closed time paths that loop back to one's own past. This leads to strange puzzles, such as the classic grandfather puzzle, where a traveller might change their own history. Most scientists believe that in a proper theory of quantum gravity, these strange chances would go away. The fact that singularities appear in Einstein's equations is actually a sign that the theory itself reaches a breaking point. At such extreme densities, quantum effects must take part. and yet scientists have not yet managed to make a single theory that joins quantum mechanics with general relativity. Many expect that once such a theory exists, it will remove singularities fully. One of the most fascinating features of a black hole is something known as the photon sphere. This is a perfectly round region around the black hole where light itself can circle in delicate and unstable loops. Imagine beams of light trapped in a ghostly racetrack around the darkness, running endless laps. For a black hole that is not spinning, this strange sphere lies at a distance equal to 1.5 times the size of the event horizon, the invisible boundary beyond which nothing can ever escape. But these orbits of light are incredibly fragile. Even the smallest push or disturbance will decide the light's fate. It will either spiral inward, swallowed forever by the black hole, or escape outward into space. Light can still break free from this sphere if it happens to be moving outward, but any ray heading inward past this invisible boundary is doomed. In spinning black holes, the situation becomes even more complicated, because the radius of the photon sphere depends on whether the light moves in the same direction as the spin or against it. This is why black holes are not just cosmic vacuum cleaners. They are places where the very rules of reality bend until they nearly snap. Here, time itself slows, space becomes twisted and stretched, and even light, the fastest thing in the universe, can be trapped in a dangerous dance with gravity. But a rotating black hole has something even stranger, a region called the ergosphere. Think of it as a distorted bubble of space and time that surrounds the black hole. In this zone, space itself is being dragged around and twisted because of the black hole's spin. This happens due to a phenomenon predicted by Albert Einstein's theory of general relativity called frame dragging. The idea is simple but mind-bending. Whenever something in the universe spins, whether it is a planet, a star, or a black hole, it tugs slightly on the fabric of space around it. For ordinary objects like Earth, this dragging is so small that we barely notice it. But near a spinning black hole, the effect becomes overwhelming. In fact, it is impossible to remain still there. To stay motionless with respect to the rest of the universe, you would need to move faster than the speed of light in the opposite direction of the black hole's spin, a task that the laws of physics forbid. The ergosphere itself is shaped like a squashed sphere. Its innermost edge is the event horizon, that dreaded point of no return, and its outer edge is known as the ergosurface. At the black hole's poles, the ergosurface and the event horizon meet, but around the equator, the ergosurface bulges outward, lying much farther from the black hole. What makes the ergosphere so remarkable is that, unlike the event horizon, it does not lock everything away forever. Light, particles, and even whole spacecraft, at least in theory, could escape from this zone. And there is something even more extraordinary. Through a process called the Penrose process, an object can enter the ergosphere and come out with more energy than it had when it went in. The extra energy is stolen directly from the black hole's spin, which means the black hole is slowly robbed of its rotational power over time. There is also an even stronger version of this energy theft, known as the Blandford-Znajek process. When extremely powerful magnetic fields are involved, this process may be the key behind the titanic energy bursts of some black holes. In fact, scientists believe it could be the reason why we see enormous high-speed jets of particles blasting out from quasars and other shining galactic centers, stretching across distances measured in millions of light-years. Orbits around a black hole also follow rules that are nothing like the familiar world of planets circling the Sun. In Isaac Newton's picture, a small object can orbit a massive body at almost any distance, provided its speed is just right. But Albert Einstein's general relativity changes this view. It says there is a final boundary for safe orbits called the innermost stable circular orbit, or ISCO. If an object drifts even a little inside this orbit, it will spiral into the black hole with no hope of return. If it drifts slightly outward, it may settle into another path, wobble between near and far points, or, if it carries enough energy, escape altogether and vanish into the far reaches of space. The location of this last safe orbit depends on how fast the black hole spins. For a non-spinning black hole, called a Schwarzschild black hole, the ISCO lies farther away. But the faster the black hole spins, the closer this orbit moves toward it, at least for objects moving in the same direction as the spin. Beyond this point lies the plunging region, the last visible frontier before total capture. In this domain, there are no safe paths left. Matter cannot orbit here, It rushes straight toward the black hole at nearly the speed of light, plunging headfirst into eternal darkness in a final, unstoppable fall. Black holes are among the strangest and most puzzling objects in the universe, so much so that for a very long time, many scientists were not even sure if they were real. Black holes are among the strangest and most puzzling objects in the universe, so much so that for a very long time, many scientists were not even sure if they were real. At first, they seemed like nothing more than strange tricks hidden inside the equations of Albert Einstein's general theory of relativity. Even Einstein himself did not think that nature could actually produce such extreme objects. He believed that if a group of particles collapsed under the pull of gravity, their spin, what scientists call angular momentum, would act like a kind of shield, keeping them orbiting at a safe distance instead of letting them collapse all the way down to a single point. Because Einstein was such a towering figure in physics, his doubts carried great weight. For many years, most researchers brushed aside any idea that pointed to black holes as real, physical objects. They treated them more as peculiar mathematical results than as things that could truly exist in space. Yet a small but determined group of scientists refused to give up. They kept arguing that black holes were not just wild fantasies on paper, but genuine parts of the universe waiting to be discovered. By the late 1960s, they had begun to win the debate, showing that nothing in the laws of physics actually stopped an event horizon, the invisible boundary that marks the point of no return, from forming. The breakthrough came when the British mathematician Roger Penrose proved that if such an event horizon formed, then a singularity, a point of infinite density where space and time themselves break down, must also form inside it. Soon after, Stephen Hawking demonstrated that singularities were not only tied to black holes, but could also appear in models of the entire universe, including the moment of the Big Bang itself. These discoveries shifted black holes from the realm of speculation into the heart of serious physics. New solutions and theories followed. The Kerr solution revealed the strange nature of rotating black holes. The no-hair theorem showed that black holes could be described with just a few simple numbers: their mass, their spin, and their electric charge. Then came the laws of black hole thermodynamics, which gave scientists a way to treat these mysterious objects as if they obeyed rules similar to heat and energy systems. Step by step, black holes became not curiosities, but central objects of study in modern science. In the real universe, the most common way a black hole forms is through the collapse of a massive star. A star spends its life balancing two powerful forces, the inward pull of gravity and the outward pressure created by the heat of nuclear fusion, the process that fuses lighter atoms into heavier ones at its core. But when a star runs out of nuclear fuel, it loses its inner pressure. If it cannot produce enough heat to fight against gravity, it begins to collapse. Sometimes, this collapse halts before a black hole can form, producing other strange but smaller objects like neutron stars or white dwarfs. The outcome depends on the mass of the remaining stellar core after the star explodes in a supernova. If the remnant core is extremely heavy, more than about 3 to 4 times the mass of our Sun, then even the pressure from tightly packed neutrons is not enough to stop the collapse. At this stage, nothing known in physics can resist the crushing gravity, and a black hole is born. The collapse of giant stars produces what are called stellar mass black holes. In the very early universe, there were stars dozens or even hundreds of times heavier than the Sun. When these enormous giants collapsed, they could create black holes up to nearly 1,000 times more massive than the Sun. These may have acted as the seeds from which the supermassive black holes at the centers of galaxies eventually grew. There is also another fascinating possibility. In the young universe, some black holes may have formed not from stars at all, but directly from the collapse of giant clouds of gas. These direct collapse black holes could have been as heavy as 100,000 suns, and they might explain the earliest quasars, the dazzling beacons of light powered by matter falling into young monster-sized black holes. The way black holes appear depends on the perspective of the observer. If you were falling in, the collapse would seem to finish in a short, definite time. But to a distant observer, the process looks very different. Because of gravitational time dilation, the falling matter seems to slow down as it nears the event horizon. Its light grows dimmer and redder, appearing to freeze and fade away before ever crossing the boundary. Although the universe today is not dense enough everywhere to create black holes easily, Conditions were very different right after the Big Bang. In those first moments, matter was packed so tightly that it may have been possible for primordial black holes to form. Ancient black holes created not from stars, but directly from the raw chaos of the early universe itself. For this to happen, however, the matter needed to clump together unevenly. If it was spread out too smoothly, no black holes could form. But small ripples in the density of the young cosmos could have allowed gravity to squeeze some regions into black holes. These could have ranged from the mass of something as tiny as a single atom to hundreds of thousands of times the mass of the Sun. Still, even with such extreme densities, the universe did not simply collapse into one colossal black hole. That is because the expansion of the universe after the Big Bang was unimaginably fast, faster than gravity could pull matter together. According to the theory of cosmic inflation, a mysterious force that acted like a repulsive kind of gravity drove space to expand at a breathtaking rate, keeping the universe from falling in on itself and shaping it into the vast cosmos we see today. The science of collapsing stars does not work in the same way for the Big Bang, because the Big Bang involved all of space itself spreading out at an unbelievably fast rate, a situation very different from a single, lonely object shrinking under gravity. Black holes are not created only from the crushing pull of gravity. In theory, they could also appear in very powerful particle crashes if the thickness of matter reached during such a collision became high enough. Yet, as of the year 2002, no one has ever found proof of such events, not directly by seeing them, nor indirectly through strange missing mass results in experiments inside particle smashers. This lack of proof suggests that there is probably a lowest mass a black hole must have before it can exist. In theory, this lowest limit is thought to be near something called the Planck mass, a very tiny but important scale where quantum effects would take over, making the predictions of Einstein's general relativity break down. If that is true, creating a black hole would be far beyond the reach of any high-energy process we could make here on Earth. However, some daring new ideas in quantum gravity suggest that this lowest mass could be much smaller. In certain ideas called brane-world models, this limit could be as low as about 1 tera-electron-volt divided by the speed of light squared. That is small enough that tiny black holes, often called micro-black holes, might, at least in theory, form when cosmic rays from space smash into Earth's air, or even inside the Large Hadron Collider at CERN. But these ideas are still very unsure, and most experts think such black holes are not likely to appear. Even if a micro-black hole could be made, the risk to Earth would be almost nothing. Calculations show that such an object would disappear in about 10 to the power of minus 25 seconds, an unimaginably short time, through a process known as Hawking radiation. Once a black hole of any size does form, it can grow by pulling in more matter. Gas, dust, and other material drifting in space can be dragged in and swallowed, slowly making the black hole heavier. This eating process may be one way some of the huge, supermassive black holes at the centers of galaxies formed, though scientists still do not know the full story. Something similar might also explain the existence of middle-sized intermediate-mass black holes found in thick star clusters called globular clusters. Black holes can also grow by joining together, crashing into other black holes, or even swallowing whole stars. In the early universe, this may have been an important way for supermassive black holes to become bigger, as smaller black holes joined again and again. In the year 1974, scientist Stephen Hawking made a shocking prediction. Black holes are not truly black. Instead, they should give off a faint glow of heat, now called Hawking radiation. Using quantum field theory on the curved space around a black hole, Hawking found that the hole should release particles in a pattern matching that of a perfect black body. Many other scientists have since supported this result using different methods. If Hawking was right, then black holes slowly lose mass over time, because this radiation carries away energy. The warmth of this radiation, known as the Hawking temperature, is linked to the black hole's surface gravity. For a simple, non-spinning black hole, the bigger its mass, the lower its temperature. Large black holes therefore give off less than smaller ones. For example, a black hole with the mass of our Sun would have a Hawking temperature of about 62 nanokelvins, far colder than the 2.7 kelvins of the cosmic microwave background that fills the universe. This means such black holes gain more mass from taking in that background radiation than they lose through Hawking radiation, so they grow instead of shrinking. To actually fade away, A black hole must be hotter than the cosmic background. That would need a mass smaller than that of our moon. A black hole that small would be tinier than 1/10 of a millimeter wide. If we go smaller still, the effect becomes extreme. A black hole with the mass of a car would be about 10 to the power of minus 24 meters wide, and would vanish in only a billionth of a second, briefly shining with more than 200 times the brightness of the sun. Shrink it further, and fading becomes even faster. A black hole with a mass of only 1 tera-electron-volt per speed of light squared would vanish in less than 10 to the power of minus 88 seconds. Some have wondered if quantum gravity could make such tiny black holes last, but present ideas give no proof for that. For star-made black holes, the ones formed by collapsing stars or bigger, Hawking radiation would be so faint that we could never see it directly from Earth. The only possible exception might be the final flash of energy in the last instant of a primordial black hole's life, when it fades completely in a burst of gamma rays. Astronomers have searched for such flashes, but so far none have been found. NASA's Fermi Gamma Ray Space Telescope, launched in the year 2008, is still looking. If Hawking radiation is real, then a black hole the mass of our Sun would take about 10 to the power of 64 years to fade away, but only once the universe has cooled enough that the cosmic background is colder than the black hole itself. A supermassive black hole weighing 100 billion suns would take about 2 times 10 to the power of 100 years. In theory, during the collapse of a giant collection of galaxies, a supercluster, a black hole might grow to 100 trillion solar masses. Even that giant would still fade away in time, over an incredible timescale of up to 10 to the power of 1006 years. Black holes, by their very nature, are masters of hiding. They do not shine, sparkle, or give out any form of radiation that we can usually see, except for the still untested Hawking radiation, which remains an interesting but theoretical idea. Because of this, scientists cannot simply look at a black hole the way we look at a star or planet. Instead, they must act like cosmic detectives, searching for indirect clues. One of the most common ways is to watch how a black hole's great pull changes the movement and behaviour of nearby stars, gas and dust. A daring step forward in the effort to see black holes more directly came from the Event Horizon Telescope, often called the EHT, a worldwide network of radio observatories working together as if they were a single Earth-sized telescope. Its mission is nothing less than to peer right up to the edge of a black hole's event horizon, the invisible border beyond which nothing can return. In the month of April, in the year 2017, the EHT began targeting the supermassive black hole at the centre of the galaxy Messier 87, a huge round galaxy in the Virgo cluster. Over a span of 10 days, 8 radio observatories placed on 6 mountains spread across 4 continents aimed their tools toward this faraway galaxy. The data they gathered were carefully studied for 2 years. Finally, in April of the year 2019, people were shown something never seen before, the very first picture of a black hole. The picture did not show the black hole itself, because a black hole stays invisible, appearing as a perfectly dark circle where light disappears forever. Instead, the EHT revealed the glowing, heated gas swirling just outside the event horizon. This gas, shining in fiery shades of orange and red, outlined the black hole's shadow against the light around it. On the 12th day of May in the year 2022, the EHT showed another historic picture, this time of Sagittarius A, the supermassive black hole at the very centre of our own Milky Way galaxy. Much like its cousin in Messier 87, Sagittarius A appeared as a glowing ring surrounding a dark centre, the result of gravity bending light around the black hole's pull. However, taking the picture of Sagittarius A was far harder. It is over 1,000 times smaller and less heavy than the Messier 87 black hole, and its surroundings are much more messy. The picture was also blurred somewhat by restless plasma between Earth and the galaxy's centre. In the finished pictures, the bottom half looked brighter than the top. This was caused by a phenomenon called Doppler beaming, when matter moving toward the observer at speeds close to that of light looks brighter than matter moving away. This bright material circles at over 1,000 kilometers per second, more than 2,200,000 miles per hour, just fast enough to resist the black hole's massive pull. For Messier 87, this meant that the EHT had captured the view almost edge-on, watching the disk of gas spin clockwise. Black holes also bend light in such extreme ways that they create a strange illusion. Even if you're looking from the side, you can still see the far side of the disk, as light curves around the black hole and escapes to your eyes. The HT's work has not stopped at pictures alone. In the year 2015, it detected magnetic fields just outside Sagittarius A's event horizon. These fields, twisted yet partly ordered, had long been expected by theory, but never seen so close to a black hole before. In April of the year 2023, astronomers reached another great step, showing for the first time the shadow of the Messier 87 black hole, together with its amazing high-energy jet of material streaming into space. Meanwhile, another groundbreaking discovery had already happened on the 14th day of September in the year 2015. The LIGO Observatory made the first ever direct detection of gravitational waves, tiny ripples in space and time itself. The signal matched perfectly with predictions for the crash and merger of two black holes, one weighing about 36 times the mass of our Sun, and the other around 29 times the Sun's mass. Just before merging, these two giants were separated by only about 350 kilometers, roughly 4 times the Schwarzschild radius for their combined mass, showing clearly that they were incredibly compact. LIGO's data even captured the ring down, the short vibration of the newly formed black hole as it settled into a steady shape. By studying the frequency and fading pattern of this signal, scientists could calculate the black hole's mass and spin, numbers that matched what computer models had predicted. This confirmed not only the presence of a photon sphere, a region where light itself can circle around, but also gave the strongest proof yet for the reality of black holes and binary black hole systems. It was also the very first time scientists had directly confirmed the existence of stellar mass black holes heavier than 25 suns. Since then, LIGO and other observatories have detected many more gravitational wave events, each one peeling back another layer of the black hole mystery. The movement of stars near the very centre of our Milky Way galaxy has given astronomers some of the strongest proof yet that an enormous invisible object is hiding there, a supermassive black hole. Since the year 1995, scientists have been carefully watching the motions of about 90 stars as they circle around an unseen point in space, a point that matches exactly with a powerful radio source known as Sagittarius A star. By studying these stars' movements and matching them to the kind of orbits first described by Johannes Kepler centuries ago, astronomers were able, in the year 1998, to figure out that the mysterious central object must have a mass equal to about 2,600,000 times the mass of our Sun. Even more amazing, this enormous mass had to be squeezed into a space no larger than about 2/100ths of a light-year across. Over the years, one particular star, named S2, has been watched closely as it completed an entire orbit around this hidden giant. Using this new and precise data, astronomers improved their measurements. They found the central mass to be about 4,300,000 times the mass of the Sun, squeezed within a region less than 2/1000ths of a light-year wide. Even though this size is still a little too large to prove beyond doubt that it is smaller than its Schwarzschild radius, the point beyond which nothing can escape, the observations leave very little room for doubt. No known object other than a supermassive black hole could pack so much mass into such a tiny space. There is also some evidence that this object has an event horizon, the invisible one-way boundary that marks the edge of a black hole, which would confirm its true nature. Because of the way angular momentum is kept in nature, gas falling toward any very massive object does not simply drop straight in. Instead, it spirals inward, forming a thin, flat, disc-like structure called an accretion disk. In artists' pictures, the black hole is often shown blocking part of this disk, but in reality the extreme bending of light, called gravitational lensing, would make the disk look strangely warped and twisted. Inside such a disk, rubbing between the swirling layers of gas causes some of the angular momentum to be pushed outward, allowing matter to spiral ever closer to the black hole. As it falls inward, gravitational energy is changed into heat, making the gas burning hot. When the central object is a neutron star or a black hole, the gas in the innermost part of the disk can move at very high speeds, producing so much rubbing that it reaches temperatures at which it shines brightly in powerful radiation, especially X-rays. This process of accretion, matter falling into the pull of a massive object, is one of the most efficient ways of producing energy in the entire universe. Up to 40% of the material's rest mass can be turned into pure radiation. By comparison, nuclear fusion in stars only releases about 0.7% of the rest mass as energy. Sometimes, these accretion disks shoot out gigantic streams of matter at nearly the speed of light, blasting away from the black hole's poles. The exact process that creates these streams is still a mystery, partly because astronomers do not yet have enough detailed data. Still, accretion onto black holes is believed to power some of the most energetic events in the universe, from the blazing centers of active galaxies to quasars, the bright beacons visible across billions of light years. X-ray binaries, in which a black hole or neutron star pulls matter from a partner star, are also powered by this process. In some cases, astronomers think that extremely bright X-ray sources, so-called ultraluminous X-ray sources, might be the accretion disks of black holes of middle size. Sometimes a star wanders too close to a supermassive black hole at the center of a galaxy and is ripped apart by the strong tidal forces. This catastrophic event, called a tidal disruption event, scatters the star's material into space, with some of it falling back to form a temporary accretion disk that shines across the whole range of light. In November of the year 2011, astronomers reported the very first direct observation of a quasar's accretion disk circling a supermassive black hole. In X-ray binaries, the presence of a normal star moving around with a compact object gives an important clue. It allows astronomers to measure the system's orbital details and estimate the mass of the hidden partner. If that mass is far greater than the maximum a neutron star can have before collapsing, a value known as the Tolman-Oppenheimer-Volkoff limit, then the object is almost certainly a black hole. The first strong candidate for a black hole found in this way was Cygnus X1, discovered in 1972 by Charles Thomas Bolton, Louise Webster, and Paul Murdin. While there was still some doubt at the time because of the heavy mass of the partner star, astronomers have since found better candidates in a class of X-ray binaries called soft X-ray transients. In these systems, the partner star is of relatively low mass, making the black hole's mass easier to measure with good accuracy. These systems go through long, quiet phases, sometimes lasting 10 to 50 years, when the accretion disk glows faintly and X-rays are barely seen. This quiet period, called quiescence, allows astronomers to study the partner star in detail. One of the most convincing examples of such a system is a black hole candidate known as V404 Cygni. Sometimes, the glowing disks of gas and dust swirling around black holes, called accretion disks, do something strange. Their X-ray light does not shine steadily, but flickers in a rhythmic pattern at certain speeds. Astronomers call these patterns quasi-periodic oscillations. They are believed to be caused by clumps of matter moving right along the very inner edge of the accretion disk, a point known as the innermost stable circular orbit. The speed of these flickers is linked to the mass of the object at the center, so by studying them, scientists have found a clever new way to estimate the mass of possible black holes. Astronomers also have a special name for galaxies that behave strangely. They call them active galaxies. These galaxies give off unusual signals such as odd patterns in their light spectrum and radio waves so powerful that they can be detected from millions of light years away. After years of study, both through theory and telescope observations, scientists have concluded that the heart of these galaxies, called the active galactic nucleus, or AGN, is often powered by a supermassive black hole. These giants can be millions, or even billions of times heavier than our Sun. In the standard picture, an AGN contains three main features: a supermassive black hole at the core, a spinning accretion disk made of gas and dust, and two thin but incredibly powerful jets of energy shooting out at right angles to the disk. While supermassive black holes are expected to be present in most active galactic nuclei, astronomers have only been able to make detailed measurements in a limited number of galaxies. Some of the most famous suspected homes of supermassive black holes include the graceful Andromeda Galaxy, the compact M32, the massive Messier 87, the bright elliptical NGC 3115, the lens-shaped NGC 3377, the spiral NGC 4258, the huge NGC 4889, the dense NGC 1277, the unusual quasar OJ 287, the distant and energetic APM 08279 plus 5255, and the beautiful Sombrero Galaxy. Today, it is widely believed that almost every galaxy, not just the active ones, hides a supermassive black hole in its centre. Observations have shown a close link between the mass of this central black hole and the way stars move in the surrounding bulge of the galaxy. This connection, known as the M-sigma relation, hints that galaxies and their central black holes may grow and change together, shaping each other's future. One of the ways astronomers can test whether a strange object is really a black hole is by looking at how its strong gravity bends light. This effect, called gravitational lensing, works much like a glass lens, bending the path of light beams passing close to it. Sometimes the bending is small, just a few arc seconds, in which case it is called weak gravitational lensing. Another type, microlensing, happens when the source of light is very far away and so small in the telescope's view that it looks like a sudden brightening instead of a clear bending. Around the turn of the new millennium, scientists found the first 3 possible black holes through microlensing. Then, in January of the year 2022, astronomers announced the first confirmed microlensing event caused by a lonely, isolated black hole. Another possible way to notice the bending of space caused by a black hole is to watch stars as they move around it. Several such possible stars are now being observed as they circle Sagittarius A, the supermassive black hole at the centre of our Milky Way. The case for stellar mass black holes, those that form when huge stars collapse, also rests on an important limit: the maximum mass a neutron star can have. This top boundary depends strongly on what we assume about the behaviour of matter under extreme density. If unusual states of matter exist, such as free quark matter, then extremely dense objects called quark stars could form. Some versions of supersymmetry suggest the existence of unusual Q stars, while other theories say that the particles that make up quarks and electrons, imagined particles called preons, might clump together into preon stars. These strange stars could copy many features of a black hole, but according to general relativity, even they have a maximum possible mass before they must collapse further. Interestingly, the density of a black hole changes with its size. A supermassive black hole, with a mass of about 100 million suns, would have an average density no greater than that of water. This is very different from a stellar black hole, which is far denser. Because of this, scientists understand the physics of forming a supermassive black hole more easily than the physics of smaller ones. Other explanations for their existence, such as a giant cluster of dark, compact objects packed together, usually fail because such arrangements are not steady over cosmic time. The fact that both stellar mass and supermassive black holes seem to exist in nature means that if black holes are not real, then our current theory of gravity, general relativity, must break down at extreme scales, possibly because of quantum effects. In some ideas of quantum gravity, the strange features of black holes, such as the event horizon and the central singularity, simply do not exist. One such idea, inspired by string theory, is the fuzzball model. In this view, what we think of as a black hole is really a tangled ball of strings with no sharp edge or singularity. Yet to a faraway observer, it would act just like a black hole predicted by Einstein's theory. Over the years, scientists have also thought up other possible objects that might look almost exactly like black holes, but work by totally different rules. These include the Graver star, the Black Star, the related Nestar, and the strange dark energy star. None of these has yet been proven to exist, but each offers an interesting alternative to the usual idea of a black hole. In the year 1971, the young physicist Stephen Hawking made a remarkable finding. Working under broad and general physical conditions, he showed that the total surface area of the event horizons of any group of classical black holes can never shrink. Even if 2 or more of these cosmic monsters crash together and merge into one, the combined surface area will still be equal to or larger than the sum of their original areas. This became known as the second law of black hole mechanics. Strangely, this rule mirrors the second law of thermodynamics, which says that the total entropy, a measure of disorder, of a closed system can never decrease. At that time, scientists believed black holes had zero entropy, much like a perfectly still object at absolute zero temperature. But if that were true, the second law of thermodynamics would collapse whenever a black hole swallowed matter full of entropy. the total disorder of the universe would drop, something nature supposedly never allows. To solve this puzzle, physicist Jacob Bekenstein boldly suggested that black holes must have entropy, and that this entropy should be directly linked to the size of their event horizon. In other words, the bigger the black hole's surface, the greater its entropy. 3 years later, in 1974, Hawking deepened the mystery. Using quantum field theory, he showed that black holes are not completely black after all. They give off a faint glow of blackbody radiation at a steady temperature, now called Hawking radiation. At first, this seemed to break Hawking's own second law of black hole mechanics, because as a black hole gives off energy, it loses mass and its event horizon shrinks. But the radiation also carries entropy. Careful calculations showed that if you add the entropy of the matter outside the black hole to 1/4 of the black hole's surface area, measured in the tiniest Planck units, the total always increases. This allowed scientists to see the first law of black hole mechanics as a mirror of the first law of thermodynamics, where mass is like energy, surface gravity is like temperature, and area is like entropy. Yet one strange feature stood out. A black hole's entropy depends on its area, not its volume. Normally, entropy grows with volume. The bigger the space, the more disorder it can hold. This oddity led physicists Gerard 't Hooft and Leonard Susskind to suggest the holographic principle, the idea that everything happening inside a region of space can be explained entirely by information stored on its boundary, much like a three-dimensional image encoded in a two-dimensional hologram. Although general relativity lets scientists perform a semi-classical calculation of black hole entropy, this is still unsatisfying from a theoretical point of view. In statistical mechanics, entropy counts the number of tiny ways a system could be arranged, while still looking the same at large scales, with the same mass, charge, temperature, and so on. But without a complete theory of quantum gravity, we cannot truly count these arrangements for a black hole. In the year 1995, physicists Andrew Strominger and Qumran Vafa made a breakthrough. In string theory, they managed to count the microstates of a special kind of supersymmetric black hole, and their number matched exactly with the Bekenstein-Hawking entropy formula. Since then, similar successes have appeared in both string theory and other quantum gravity ideas, such as loop quantum gravity. Still, a black hole reveals only a few simple facts about itself: its mass, its electric charge, and its spin. Almost all other information about the matter that formed it seems to be lost. As long as black holes were thought to last forever, this was not such a problem. The missing information could be imagined as hidden inside, unreachable from the outside, yet somehow shown on the event horizon in line with the holographic principle. But Hawking radiation changes everything. Black holes slowly fade away, and their radiation seems to carry no details about what fell in. If the black hole completely disappears, that information seems to vanish from the universe, a situation known as the black hole information paradox. In quantum mechanics, losing information is a very serious matter. It means breaking a rule called unitarity, which guarantees that processes can always be reversed in principle. Some argue that breaking unitarity would also mean breaking the law of conservation of energy, though others disagree. Over the past few years, evidence has been building that a full quantum gravity theory may, in fact, save both unitarity and information. One possible answer is called black hole complementarity, the idea that the two descriptions from outside and inside the black hole can both be correct without conflict. But in the year 2012, a new twist appeared: the firewall paradox. This paradox, meant to challenge complementarity, uses quantum field theory and curved spacetime to show a troubling situation. In Hawking's view, each bit of Hawking radiation comes from a pair of linked particles. One escapes to infinity, the other falls inside. If a black hole formed at some finite time in the past and will fully evaporate in a finite future time, it will give off only a limited amount of information in its Hawking radiation. According to the work of physicists like Don Page and Leonard Susskind, there will come a moment when a newly emitted particle must be linked with all the Hawking radiation that has already escaped. But here lies the paradox. The rule of monogamy of entanglement says a particle cannot be fully linked with two different systems at once. Yet in this case, the outgoing particle would have to be linked both with its partner, falling into the black hole, and with the earlier radiation. This contradiction forces physicists to consider giving up one of three cherished principles: Einstein's equivalence principle, unitarity, or local quantum field theory. One bold solution, which breaks the equivalence principle, is the idea of a firewall, a burning wall of energy at the event horizon that would destroy anything falling in. Whether any of these principles must be given up is still strongly debated, and the final answer remains one of the greatest open questions in physics. In the grand story of the universe, there is a strange and exciting idea in cosmology: the possibility that primordial black holes exist. Scientists often shorten this name to PBHs. These are not the usual black holes we know, which form billions of years after stars live and die. Instead, these are black holes that might have been born in the very first instant of cosmic history, right after the universe exploded into being in the Big Bang. If true, it would mean that black holes appeared before even the very first stars were born. During those earliest moments, especially in the short period known as the inflationary era, and later when the young universe was filled mostly with blazing radiation, space was wild and chaotic. Some regions of matter may have been unbelievably dense, so crowded with particles that gravity had no choice but to crush them into black holes. This was a very different process from what happens today, where black holes usually come from the death of a giant star in a fiery supernova blast. In this ancient case, no star was required, only the extreme density of the baby universe itself. Because they were born long before the first stars, primordial black holes could come in sizes and weights far outside the narrow range we see for modern black holes that form from stars. The idea first appeared in the year 1966, when two Soviet scientists, Yakov Zeldovich and Igor Novikov, suggested that such objects could exist. A few years later, in the year 1971, a young physicist named Stephen Hawking studied the idea more deeply and carried out the first careful calculations. Yet even after more than 50 years, primordial black holes remain a mystery. No one has been able to prove that they truly exist. In September of the year 2022, some scientists proposed a bold idea. Perhaps primordial black holes could explain one of the James Webb Space Telescope's most shocking discoveries: the presence of enormous galaxies very early in time, galaxies that seemed far too big to exist so soon after the Big Bang. For many decades, researchers have also wondered if primordial black holes might solve an even deeper puzzle: the riddle of dark matter, the invisible substance that makes up most of the universe's mass but gives off no light. Some scientists believe that primordial black holes could be not just part of dark matter, but perhaps its main ingredient, or even its only ingredient. This thought became more popular after two major discoveries: the detection of gravitational waves by the LIGO and Virgo observatories, and James Webb's view of massive ancient galaxies. At first, scientists assumed that most primordial black holes would have nearly the same mass, what they call a monochromatic distribution. But the data from LIGO and Virgo proved otherwise. The black holes they detected had a wide range of masses. Scientists describe this distribution as Platy-Curtis, which is just a technical way of saying the masses were spread out broadly. Webb's surprising discovery of very large galaxies early in time seemed to point in the same direction. Modern studies now suggest that primordial black holes could come in many different sizes, with the most common weighing about the same as our Sun. Some of these black holes might be unimaginably tiny in size yet still incredibly heavy. For example, a primordial black hole could have the weight of a giant asteroid while being no bigger than a single hydrogen atom. These strange objects would race through space at enormous speeds. At any given moment, one could even be drifting through our solar system. Most of the time, they would pass straight through stars without doing much harm, slipping through like a bullet through a cloud. But if one slowed down enough, a star could capture it. Stephen Hawking once suggested that even our Sun might be hiding one of these miniature black holes deep inside its core. Depending on the theory, the first primordial black holes could have been born with masses ranging anywhere from a tiny 10 to the power of -8 kilograms, objects called Planck relics, all the way up to thousands of times heavier than our Sun. However, those with masses below 10 to the power of 12 kilograms would have already evaporated into nothing because of a strange process known as Hawking radiation. They would have vanished long before the present age of the universe. Primordial black holes are thought to be made of non-baryonic matter, meaning they are not built from the same particles that make up ordinary atoms. This is part of the reason why they are such attractive candidates for dark matter. They might also have acted as the seeds from which the largest black holes in the centres of galaxies grew, as well as the intermediate mass black holes scattered across the cosmos. PBHs also belong to a larger family of objects known as massive compact halo objects, or MACHOs. They fit many of the rules scientists expect of dark matter. They almost never collide with one another. They are stable if they are heavy enough. They move slower than light but still with significant speed, and they would have formed extremely early in cosmic history, possibly in less than 1 second after the Big Bang. Still, not everyone agrees. Some astronomical measurements place very tight limits on their numbers, suggesting that they cannot make up most of the dark matter across much of the possible mass range. Even so, new studies have reopened the debate. Some researchers think primordial black holes might gather in clusters, with one central black hole weighing about 30 times the mass of the Sun, surrounded by a family of smaller ones. In March of the year 2016, just 1 month after LIGO and Virgo announced their very first detection of gravitational waves, from 2 black holes, each around 30 times the mass of the Sun colliding together, 3 different research groups suggested that those black holes could have been primordial in origin. 2 of the groups argued that the rate of such mergers fit well with the universe, where dark matter was made entirely of primordial black holes, especially if they were clustered inside faint dwarf galaxies or dense star clusters. The third group disagreed, saying primordial black holes could not account for more than 1% of dark matter. Still, the unexpectedly large size of LIGO's black holes reignited interest in primordial black holes, weighing between 1 and 100 solar masses. The debate is far from settled. Other studies, such as the lack of microlensing effects on background stars, patterns seen in the faint glow of the cosmic microwave background, the tiny size of faint dwarf galaxies, and the missing signals of X-rays or radio waves near the heart of our Milky Way, seem to challenge the idea that primordial black holes exist in great numbers. In May 2016, Alexander Kashlinsky suggested that certain patterns in the gamma-ray and X-ray backgrounds could be explained by primordial black holes of similar masses if they are as common as dark matter. In August 2019, a study suggested that dark matter could be entirely made of primordial black holes with asteroid-like masses between 3.5 times 10 to the power of minus 17 and 4 times 10 to the power of minus 12 solar masses, or between 7 times 10 to the power of 13 and 8 times 10 to the power of 18 kilograms. A month later, in September 2019, James Unwin and Jakob Schultz proposed that an object with between 5 and 15 times the mass of Earth, but only the size of a tennis ball, could be hiding in the outer Kuiper belt. This could explain certain unusual orbital movements that scientists had previously thought were caused by a mysterious 9th planet. In October 2019, Derek Inman and Yassine Ali Haimoud found that the small speeds created by cosmic structure formation were not large enough to change the limits set by observations of the cosmic microwave background. In September 2021, the Nanograv collaboration announced that they had detected a low-frequency signal that might be linked to gravitational waves from primordial black holes. Then, in September 2022, the theory was once again connected to Webb's discovery of unusually large galaxies at very early times in the universe. On the 26th of November 2023, scientists reported the first evidence of an overmassive black hole galaxy, an object called UHZ-1. This galaxy, observed with the Chandra X-ray Observatory and the James Webb Space Telescope, seems to have formed its central black hole not from the death of a star, but from the direct collapse of massive gas clouds, another way to create a giant black hole. In 2024, Bernard Carr and his colleagues published a review concluding that primordial black holes likely formed during the quantum chromodynamics epoch, less than 10 to the power of minus 5 seconds after the Big Bang. They argued that the primordial black holes existing today should have a wide mass distribution with several peaks, the most important one being around 1 solar mass. In the unimaginably young universe, less than 1 single second after the Big Bang, conditions may have been so extreme that strange and powerful objects called primordial black holes could have formed. This was during 2 possible early chapters of cosmic history, either the mysterious inflationary era, when space itself expanded faster than the speed of light, or the later radiation-dominated era, when the universe was filled with blazing light and high-energy particles. The main ingredient needed to make a primordial black hole is a patch of the universe that is much denser than the space around it. If that patch is heavy enough, gravity takes over, crushing it into a black hole without the need for a dying star. Scientists call these differences in density contrasts, and several early universe processes could create them. One such process is called axion inflation, a theory where a particle known as the axion acts like the inflaton field that powered inflation. Because of the moment in cosmic history when it appears, the axion field gently vibrates at the lowest possible energy level, and those vibrations can cause ripples in the energy density of the universe. Those ripples, in turn, could have been seeds for primordial black holes. Another possibility is tied to a stage called reheating, the short but important bridge between the end of inflation and the beginning of the hot, dense, light-filled era. During reheating, the inflaton field breaks down into other particles. These particles start colliding and sharing energy until they reach thermal balance. But if that balancing act is incomplete, lumps of extra dense matter can form, and if those lumps are large enough, they could collapse into primordial black holes. Primordial black holes are also connected to the Great Dark Matter mystery, first pointed out in the year 1933 by Swiss-American astronomer Fritz Zwicky. He noticed that galaxies and clusters were moving as if they were being pulled by an invisible mass, something far heavier than all the stars combined. If primordial black holes made up all, or even a large part, of dark matter, they could explain the strange gravitational behavior of galaxies and galaxy clusters. Unlike one popular dark matter candidate, weakly interacting massive particles or WIMPs, primordial black holes could also produce gravitational waves that push normal matter. They might even explain certain cases of gravitational lensing, where light from distant objects is bent more strongly than ordinary matter could explain. And because primordial black holes do not have to be tiny, they could be of almost any size. They may have helped shape galaxies earlier than astronomers once thought possible. There is also something called the cosmological domain wall problem, proposed in the year 1974 by Soviet physicist Yakov Zeldovich. Domain walls are imaginary structures that could have formed when the early universe went through phase changes, like cosmic ice, freezing into different patches. If they had been created, their enormous energy could have caused serious problems for the growth of the universe. Primordial black holes might solve this in several ways. They could stop domain walls from forming in the first place by pulling matter into clumps with their gravity. If domain walls did form, gravitational pulls from primordial black holes could have caused them to collapse into new black holes. And if primordial black holes in the mass range of 10 to the power of 12 to 10 to the power of 13 kilograms were ever detected, they could contain exactly the right amount of mass to make up all the dark matter, without causing the problems domain walls would bring. Zeldovich also suggested another puzzle in the late 1970s, the cosmological monopole problem. Magnetic monopoles are imaginary particles with only one magnetic pole, north or south, instead of both. The trouble is, we do not see them today, even though certain theories predict they should exist. Primordial black holes could explain this absence. If monopoles did exist in the early universe, they could have been swallowed by primordial black holes, or the black hole's gravity could have caused matter to clump in ways that reduced monopole density until they were effectively gone. General relativity predicts that the smallest primordial black holes should have completely vanished by now, disappearing in bursts of radiation. But there is a twist. If our universe has a hidden fourth spatial dimension, as some string theory models suggest, it could slow down this disappearance dramatically. In this case, the energy stored in that fourth dimension would give the black hole extra mass when viewed in our familiar four-dimensional space-time. This might mean that there are still several thousand primordial black holes quietly drifting in our own Milky Way galaxy today. To test this possibility, scientists are turning to the Fermi Gamma Ray Space Telescope, launched into orbit by NASA on June 11, 2008. If the telescope spots tiny, distinct interference patterns in gamma-ray bursts, it could become the first indirect clue that primordial black holes, and even extra dimensions, are real. Over the years, scientists have used many clever ways to put limits on how many primordial black holes might exist, and how heavy they could be. These strange objects, if real, could range from tiny specks with the mass of a mountain to enormous giants weighing as much as many stars. One of the most famous ideas about primordial black holes comes from the British physicist Stephen Hawking, who, in the year 1974, proposed something revolutionary. Black holes are not completely black. Instead, they slowly release a faint form of energy, now known as Hawking radiation. According to Hawking's theory, all black holes lose mass over time by giving off this radiation. The smaller the black hole, the faster it loses mass, a bit like a block of ice melting more quickly when it's tiny rather than huge. If a black hole is extremely small, it can reach a runaway stage of evaporation, releasing an enormous burst of energy in its final moments. In fact, such an explosion would rival the force of a hydrogen bomb, producing millions of megatons of energy. Ordinary black holes, like those formed from collapsing stars, are far too massive to vanish within the lifetime of the universe. For example, a black hole about 3 times the mass of our Sun would take roughly 10 to the power of 69 years to disappear, far, far longer than the universe's current age. But primordial black holes are special because they are not made from dying stars. They could be born with any mass at all, even very tiny ones. A primordial black hole with a mass of about 100 billion kilograms would live for about as long as the universe has existed so far. If many such black holes were born in the Big Bang, some nearby ones should be finishing their lives right now, releasing brilliant bursts of radiation in our Milky Way. NASA's Fermi Gamma Ray Space Telescope, launched in June 2008, has been scanning the skies for exactly these kinds of final explosions. From its observations, scientists concluded that less than 1% of all dark matter could be made of primordial black holes, with masses up to about 10 trillion kilograms. These tiny black holes, if they exist, could also have changed the very chemistry of the early universe. Their energy output might have influenced the Big Bang's element-making process, altering how much hydrogen, helium, and other light elements were formed. If Hawking radiation does not really happen, if nature has found a way to silence it, then primordial black holes would be incredibly hard to detect. Being so small, they would not pull strongly on nearby stars or planets, and they would remain almost invisible against the cosmic background. Primordial black holes could also leave marks on the cosmic microwave background, the faint glow left from the Big Bang. In the early universe, they would pull in surrounding matter, releasing energy that could change the timeline of recombination when the first atoms formed. The European Space Agency's Planck satellite has studied this in detail, ruling out the idea that black holes weighing between 100 and 10,000 times the mass of the Sun could make up a major part of dark matter, at least in the simplest models. If dark matter is made of weakly interacting massive particles, or WIMPs, then primordial black holes could gather halos of these particles around them. As WIMPs collide and destroy each other, they would give off gamma rays. Telescopes like Fermi might detect these as mysterious signals from space. In the coming years, a new generation of observatories will tighten the search. The Square Kilometre Array, a massive radio telescope, will look for the effects of primordial black holes on the universe's reionization period, the time when the first stars lit up the cosmos. Gravitational wave detectors like LIGO, Virgo, and future observatories could find black hole mergers whose masses do not match anything expected from normal stars. Discovering a black hole smaller than about 1.4 times the Sun's mass would be a major clue that it is primordial. The Laser Interferometer Space Antenna, or LISA, and pulsar timing arrays will study the background hum of gravitational waves made by ancient black hole pairs still orbiting each other. Observations of faint dwarf galaxies could reveal whether they hide many primordial black holes in their dark, matter-rich centers. Tracking the positions and speeds of stars in our Milky Way might uncover the subtle pull of a nearby primordial black hole. In theory, if a tiny primordial black hole were to pass through the Earth, it could create a ripple in the form of a faint sound wave, an acoustic signal that might be picked up by sensitive instruments. Because such a black hole would be unimaginably small, yet packed with an enormous amount of mass, it would not slow down or break apart. Instead, it would pierce straight through the planet, leaving behind hardly a mark, like a ghostly bullet passing through mist. If one of these black holes were to cross a star, the effect would be even more dramatic. The star's glowing surface could shiver and ripple, almost like the surface of a pond after a stone has been tossed into it. These vibrations would not remain hidden. They would travel outward, and astronomers could detect them with careful measurements. Another way to track these mysterious objects is by watching the steady light of quasars, those brilliant faraway beacons powered by supermassive black holes at the centres of galaxies. If a primordial black hole were to drift in front of one, its gravity could bend the light ever so slightly. This bending, called gravitational microlensing, would appear as a small but measurable distortion, a cosmic fingerprint revealing the presence of an otherwise invisible traveller. Even the quiet, predictable orbits of planets within our own solar system, like the steady path of Mars, might betray the passing of a black hole. If one slipped nearby, the planet's motion could suddenly shift, as if tugged by an invisible hand. None of the great observatories humans have built were designed with the sole purpose of hunting primordial black holes. Yet the treasure troves of data they collect might still hold secrets waiting to be uncovered. The LIGO and Virgo detectors, which are famous for capturing the first ripples of gravitational waves in the year 2015, might one day notice a black hole signal that does not match the usual story of collapsing stars. Such a detection would be historic, the very first direct proof of these ancient cosmic relics. Looking ahead, future instruments with poetic names like the Cosmic Explorer, the Einstein Telescope, and the EDGE mission will be even more powerful, perhaps sensitive enough to finally solve the mystery. There is also the Nanograv project, which listens for the deep, slow rumblings of spacetime itself. If its puzzling background signals turn out to be gravitational waves from black holes smaller than the Sun, then humanity might have to rewrite the entire story of the universe's earliest moments. The Nancy Grace Roman Space Telescope, once known as WFIRST, will soon open its eye to the heavens. This powerful space observatory will peer deeper into cosmic mysteries and will be able to search for primordial black holes in new ways. One of its clever techniques, called astrometric lensing, works like this. Imagine a familiar star glowing quietly in the night sky. Now picture a hidden object, perhaps a black hole, gliding across its path. As it passes in front, the star's position seems to wobble ever so slightly, by just a few millionths of an arc-second. This shift is so tiny it is almost beyond imagination, yet it is precisely the kind of subtle movement the Roman telescope will be able to detect. On Earth, the Virasey-Rubin Observatory, which once carried the name Large Synoptic Survey Telescope, will play a different but equally vital role. Its vast eye will measure the spread of masses among strange and unseen objects, using microlensing to spot the telltale brightening of background stars when hidden objects pass in front of them. With this, it can reveal both the featherlight and the heavyweights of the cosmos. Even more, the Rubin Observatory might catch sight of kilonovae, dazzling explosions caused by the collision of neutron stars. Some of these cosmic fireworks may appear without the expected gravitational wave ripples. Such silent kilonovae could, intriguingly, point toward primordial black holes. Then there is the NGVLA, or Next Generation Very Large Array, a sprawling network of radio telescopes that will take humanity's reach even farther. Compared to today's nanograv, it will sharpen the limits on gravitational wave signals by a factor of 10. With such extraordinary sensitivity, NGVLA could finally confirm the true origin of the faint background hum that Nanograv has already detected. Was it born from primordial black holes? Or does it come from some other unknown cosmic engine? This new instrument may at last give us the answer. These telescopes will also collect huge amounts of information about fast radio bursts, sudden, mysterious flashes of radio energy that streak across the universe. If these bursts show signs of bending or distortion, they could reveal black holes working in secret as invisible cosmic magnifying glasses. Another key battleground in the search for primordial black holes lies in the realm of gamma rays, the most powerful form of light known. So far, the region of mega-electron-volt gamma rays has hardly been explored, but upcoming experiments promise to change that. These could place strong limits on the number of primordial black holes with asteroid-like masses. In theory, black holes with masses around 5 times 10 to the 19th power of the Sun's mass should slowly evaporate, releasing tera-electron-volt gamma rays in the process. These emissions would appear as sudden bursts scattered evenly across the sky, a glittering spray of cosmic sparks that wide-field observatories are perfectly designed to spot. Even observatories with narrower views of the heavens can contribute. Their astonishing sensitivity to tera-electron-volt cosmic rays allows them to set strict limits on how often such bursts occur. By weaving together results from all of these efforts, from gravitational waves to gamma rays, from subtle star wobbles to explosive kilonovae, scientists hope to piece together the truth. If primordial black holes are real, these combined tools may not only prove their existence, but also reveal how many of them wander the vast cosmic sea. A stellar black hole is born in one of the most breathtaking and violent ways the universe can offer. Imagine a star far bigger than our Sun, burning brightly for millions of years. Eventually, this enormous star uses up all of its nuclear fuel, the very energy that once pushed outward and held back the crushing force of gravity. Once the fuel is gone, the star loses the battle with its own weight. Its heart, the dense core at the center, collapses inward, squeezed by unstoppable gravity. This collapse, known as a gravitational collapse, crushes the star so completely that it creates one of the strangest and most powerful objects in existence, a black hole. These stellar black holes are not the monstrous giants that lurk at the centers of galaxies. Instead, they usually weigh between 5 and a few dozen times the weight of the Sun. Yet even though they are small compared to supermassive black holes, they are still unimaginably powerful. A stellar black hole is what remains after a massive star ends its life in a spectacular explosion called a supernova. During this cosmic blast, the outer layers of the star are thrown far into space, while the inner core falls inward. Sometimes the explosion is so powerful that it gives off sudden flashes of gamma rays, the most energetic type of light known in the universe. Because they are born from collapsing stars, stellar black holes are sometimes called collapsers, short for collapsed stars. Despite the violent way they are made, black holes are surprisingly simple. According to a rule in physics often called the no-hair theorem, a black hole can be described completely by just 3 features: its weight, its electric charge, and its spin, how fast it is turning. If the parent star was spinning, as nearly all stars do, the black hole will inherit that spin and continue rotating. The birth of a black hole is simply one possible ending in the life cycle of massive stars. As long as a star is burning fuel in its core, it balances 2 forces, the outward push of energy and the inward pull of gravity. But when the fuel runs out, gravity wins. The star collapses inward, and depending on how heavy the leftover core is, several endings are possible. It may become a white dwarf, or, if heavier, a neutron star, both of which are incredibly dense remnants. In extremely rare and still uncertain situations, the core may even collapse into a quark star, made of the tiniest building blocks of matter called quarks. But if the core is too heavy, it crosses a deadly threshold called the Tolman-Oppenheimer-Volkoff limit, or TOVY limit for short. Beyond this point, no force in the universe can stop gravity from crushing the core into a black hole. Back in the year 1939, scientists estimated this TOV limit to be only about 0.7 times the weight of the Sun. Later research, including a major study in the year 1996, suggested the real limit is more likely somewhere between 1.5 and 3 times the weight of the Sun. One of the heaviest neutron stars ever found is known as PSR-J 0740+6620, discovered in September of the year 2019. It weighs about 2.14 times the weight of the Sun, very close to the tipping point where a neutron star could collapse into a black hole. Albert Einstein's theory of general relativity says that black holes can, in theory, exist at any size, from incredibly tiny to unimaginably huge. But for a black hole to form naturally from a star, the leftover mass must be at least a few times the weight of the Sun. Anything smaller than that cannot be made by stars. If black holes smaller than this do exist, they must have formed in the very earliest moments after the Big Bang. These ancient objects are called primordial black holes. Until the year 2016, the heaviest stellar black hole known had a weight of about 15 2/3 times the weight of the Sun. But in September of the year 2015, scientists made an astonishing discovery. They detected gravitational waves, ripples in the very fabric of space and time, caused by 2 stellar black holes colliding and merging. The final black hole born from this cosmic crash weighed about 62 times the mass of the Sun. This was one of the first clear and undeniable pieces of proof that black holes are real and that they can grow larger by merging with one another. Later, in June of the year 2020, astronomers announced another remarkable finding. the smallest stellar black hole ever detected up to that time. It belonged to a binary or double star system called 2MASS J 052155658 plus 4 359220. This tiny black hole weighed only about 3.3 times the weight of the Sun, and its width was just 19.5 kilometers across, smaller than the size of many cities on Earth. Besides stellar black holes, scientists recognize two other main types. There are intermediate mass black holes, which may lurk in the centers of globular clusters, tight spherical gatherings of stars. Then there are supermassive black holes, the titans at the hearts of nearly every galaxy, including our Milky Way. These giants can weigh millions or even billions of times more than the Sun. Sometimes, a stellar black hole and a normal star form a kind of cosmic partnership in a binary system. When they orbit close together, the black hole can pull material away from its companion star. This stolen gas swirls into a glowing disk around the black hole, heating up to hundreds of millions of degrees. At such extreme temperatures, the matter shines in X-rays, which astronomers can detect with special space telescopes. Even though the black hole itself is invisible, these X-rays betray its presence. Neutron stars and black holes can behave in similar ways, especially when they are feeding on matter from a nearby star. To tell them apart, scientists carefully measure their weight. All known neutron stars weigh less than 3 times the mass of the Sun. So, if an object is heavier than that, and does not behave like a neutron star, astronomers are confident it must be a black hole. Sometimes, scientists find these binary star systems far above or below the flat disk of our Milky Way galaxy, in places where they normally should not be. Astronomers believe this strange placement is caused by something called a natal kick. This is a powerful jolt that happens when a black hole is born in a violent explosion, launching it out of its birthplace like a cosmic cannonball. What makes this story fascinating is that black holes seem to get kicks, much like neutron stars do, even though black holes are far heavier. At first, you might imagine that because black holes carry more weight, they should not move very fast after being kicked. But in reality, they often do. One idea to explain this surprising behavior is that when a star collapses to form a black hole, it does not throw out all of its outer layers in a perfectly even way. Some of that matter falls back onto the newborn black hole, giving it an extra shove, like the final boost from a rocket engine that makes it move faster through space. Scientists also believe that not all black holes can be created in the same way. The way stars live and die suggests that there are special no-go zones for black hole birth. These are called mass gaps, and they appear both at the lighter end and at the heavier end of the black hole weight scale. The first puzzle is the lower mass gap, which lies between about 2 and 5 times the mass of our Sun. Strangely, very few black holes are found in this range, even though this is just above the heaviest neutron stars we know. Some researchers argue that this gap is real, while others think it may simply be that we have not yet discovered enough black holes in that range. Another possibility is that black holes of this weight do not form directly from collapsing stars, but rather from the merger of 2 neutron stars joining together. This is where the LIGO and Virgo observatories play a key role. These are enormous instruments that listen to the universe by detecting gravitational waves, tiny ripples in the fabric of space caused by giant cosmic crashes. So far, they have recorded 3 events that may involve black holes sitting right inside this lower mass gap. A further clue comes from a curious star system, where a bright, fast-spinning star appears to be circling an invisible partner. This unseen object does not give off light, not even X-rays, but seems to weigh about 3.3 times the mass of the Sun. That suggests it might be a quiet, low-mass black hole that is not currently feeding on matter, which would explain why it stays hidden. If so, there may be many more such silent black holes scattered across our galaxy, waiting to be uncovered. Now let us move to the upper mass gap, another strange missing region in the black hole weight chart. This gap is thought to stretch roughly between 50 and 150 times the mass of the Sun, though some scientists place it more narrowly between 52 and 133 solar masses. This gap is linked to one of the most violent explosions in the cosmos, called a pair instability supernova. In this type of event, a massive star becomes so hot and energetic that gamma rays within it slam into atomic particles, upsetting the delicate balance of pressure holding the star up. As a result, the core collapses and the star detonates in a titanic explosion that tears it apart completely, leaving behind no black hole at all. Such explosions only happen in extremely massive stars, those weighing between about 130 and 250 times the Sun's mass. They occur most often in stars made almost entirely of hydrogen and helium. These were the kinds of stars that lived billions of years ago, in the earliest ages of the universe. Astronomers call them Population 3 stars, believed to be the very first stars that ever shone. Some newer theories suggest that the upper mass gap might begin at a lower point, perhaps even at 45 solar masses, due to a process known as pair instability pulsational mass loss. In this stage, a star sheds large amounts of material in giant bursts before it even explodes. For stars that do not spin, the lower edge of the gap might actually rise as high as 60 times the mass of the Sun. Another possibility is that extremely heavy star cores, those weighing more than 133 solar masses, might skip the explosion altogether and collapse straight into black holes. If that is the case, then we would not expect to see the glowing remains of a supernova, which would make such events far harder to detect. This idea also suggests that the upper mass gap may mark the limit where the normal birth of black holes comes to a stop. A few years ago, astronomers studying a system called LB1 thought they had discovered a black hole of about 70 times the mass of the Sun, right in the heart of the upper mass gap. If true, it would have been a groundbreaking find. But later studies cast doubt on that conclusion, and it now seems likely that the object was not a black hole after all. Even so, there is another path into the mass gaps. Black holes might not be born directly in these ranges, but they can still arrive there by merging. When two smaller black holes collide and fuse, the new black hole that forms can easily land right inside a gap. Meanwhile, closer to home, our own Milky Way galaxy is thought to contain thousands, perhaps even millions, of stellar mass black holes. These are black holes born from dying massive stars, not to be confused with the supermassive black hole that dominates the very centre of our galaxy. Many stellar mass black holes are found in X-ray binary systems, where a black hole pulls matter away from a companion star. As this material spirals inward, it heats up and forms a glowing disk that shines brightly in X-rays, making the system easier to detect. The black holes in these systems are usually measured at between about 3 and more than 12 times the mass of the Sun. Supermassive black holes are the true giants of the universe, the biggest and most powerful kind of black holes that humanity has discovered so far. To get a sense of their size, think of this. Some of them weigh as much as hundreds of thousands, millions, or even billions of suns all put together. Imagine trying to squeeze the weight of 1 billion suns into a region of space smaller than a galaxy. It sounds impossible. Yet that is exactly what a supermassive black hole is. Black holes themselves are already some of the strangest and most mysterious things in all of space. They are born when a huge amount of matter collapses in on itself under its own gravity. This collapse creates a region where gravity becomes so powerful that nothing, not even light, the fastest traveller in the universe, can escape. Because light cannot get out, black holes appear completely black, like invisible traps hidden in the night sky. Even though we cannot see them directly, scientists can find their locations by watching how nearby stars, glowing gas and beams of light bend and swirl around them. Over many decades of study, astronomers have found strong evidence that almost every large galaxy in the universe hides a supermassive black hole at its very heart. Our own Milky Way galaxy is no exception. At its centre lies a giant black hole known as Sagittarius A star. It does not shine by itself, but when clouds of gas and dust fall into it, they heat up to extreme temperatures and release powerful bursts of energy, flashes that our telescopes can pick up across space. When matter such as gas and dust falls toward a supermassive black hole, it does not simply drop straight in. Instead, it forms a swirling disk, spinning faster and faster as it draws closer. This disk becomes unimaginably hot and produces blinding streams of energy. These cosmic light shows are so dazzling that astronomers call them active galactic centers. In the most extreme cases, the brilliance of these centers grows so intense that they are called quasars, the brightest beacons in the entire universe. A single quasar can shine more brightly than every star in its galaxy combined. Not long ago, something once thought impossible became reality. Using a worldwide network of powerful radio telescopes known as the Event Horizon Telescope, scientists captured the very first images of supermassive black holes. One image showed the giant black hole at the centre of the galaxy Messier 87, while another revealed the shadow of our own Sagittarius A star, sitting deep in the heart of the Milky Way. To earn the name supermassive, a black hole must weigh at least 100,000 times more than the Sun. But most are much heavier, millions, even billions of times heavier. Yet here is something surprising. Despite their monstrous weight, supermassive black holes are not as dense as you might imagine. If you could spread their mass evenly within their invisible boundary, called the event horizon, their average thickness might actually be less than water. This happens because as a black hole grows heavier, its size grows even faster, spreading its weight over a much larger space. Here is a thought experiment. Imagine a black hole that does not spin and carries no electric charge. If it weighed the same as 1 billion suns, its event horizon, the edge of no return, would be nearly as wide as the orbit of Uranus, the seventh planet from the Sun. That is about 19 times farther away than the distance from Earth to the Sun. And then, beyond the supermassive ones, exist the ultimate monsters, ultramassive black holes. These make even the biggest supermassive black holes look small. They can weigh more than 5 billion suns. Some of the largest examples are believed to sit at the centres of galaxies such as TON 618, NGC 1666, ESO 444, 46, and NGC 4889. Most scientists once thought there was a natural upper limit to how heavy a black hole could become, around 50 billion suns. But in the year 2020, a new study challenged that belief, suggesting that even larger black holes might exist. These hypothetical monsters were given a fitting name, stupendously large black holes or slabs. According to this idea, slabs could weigh more than 100 billion suns. One possible example may lurk at the centre of a group of galaxies known as Phoenix A. The story of how scientists first discovered these cosmic wonders is just as fascinating as the objects themselves. In the year 1963, a Dutch-American astronomer named Martin Schmidt was studying a peculiar object known as 3C 273. At first, people thought it was a strange kind of star, but when Schmidt carefully examined its light, he noticed it was redshifted, meaning it was moving away from Earth at tremendous speed. According to Hubble's law, that meant the object was billions of light years away. Yet even at that distance, it was shining as brightly as hundreds of entire galaxies put together. Scientists gave these mysterious objects a new name, quasars. By the following year, 1964, researchers had identified 4 quasars. Each of them was astonishingly small, no larger than about 3 light-years across, but they gave off mind-bending amounts of energy. Something extraordinarily powerful had to be fueling them. In the early 1960s, 2 scientists, Fred Hoyle and W.A. Fowler, suggested a bold idea. They proposed that quasars might be powered by enormous supermassive stars burning hydrogen at their cores. These stars, they thought, could weigh anywhere between 100,000 and 1 billion suns. But there was a flaw. The legendary physicist Richard Feynman pointed out that stars larger than a certain size would not remain stable. They would collapse under their own gravity, becoming black holes unless some unknown force prevented it. Later, Fowler suggested that perhaps these stars could go through repeated cycles of collapsing and exploding, releasing bursts of energy that might explain the dazzling light of quasars. In the year 1972, 2 scientists named Appenzeller and Fricke used computer models to test this idea. They found that even if a supermassive star tried to burn its fuel, it would still, in the end, fall in on itself and turn into a black hole. One of their models studied a star with 750,000 times the weight of the Sun, and sure enough, it became a black hole. Back in 1964, 2 brilliant thinkers, Edwin E. Salpeter and Yakov Zeldovich, suggested that the strong power of quasars might come from matter falling into a giant black hole. They guessed that to make such power, the black hole would need to be about 100 million times heavier than our Sun. Then, in 1969, another scientist named Donald Lynden Bell added to this idea. He explained that gas falling toward a massive object like a black hole would not just drop straight in, it would spin around and form a flat disk, like water swirling down a drain. This spinning disk would slowly be pulled in, giving off power along the way. Lyndon Bell also noticed that many nearby galaxies had faint centers, which meant they might once have been quasars that had gone quiet. Meanwhile, in the year 1967, two researchers named Martin Ryle and Malcolm Longair came up with another thought. They said that strong radio waves coming from faraway galaxies could be explained by particles being shot out of the galaxies at almost the speed of light. Later, in 1973, they joined with Peter Scheuer and suggested that the power for these fast jets might come from the dense centers of galaxies, maybe from the great pull of supermassive black holes. In 1970, scientists Arthur M. Wolf and Geoffrey Burbidge studied elliptical galaxies, those that are round or oval in shape. They noticed that stars near the centers of these galaxies were moving much faster than expected. The only answer was that there must be a huge amount of hidden weight at the center, much more than could be explained by stars alone. They decided that it could be one gigantic black hole, as heavy as 10 billion suns, or a group of many smaller black holes, each less than 1,000 times the mass of the Sun. Stronger proof came in the year 1978, when astronomers studied the elliptical galaxy called Messier 87. They found signs of a dark, massive object in the center, guessed to be 5 billion times the mass of the Sun. Soon after, similar signs were found in other galaxies too, including the Andromeda Galaxy in 1984 and the Sombrero Galaxy in 1988. Then, in 1971, Donald Lyndon Bell and Martin Rees made a bold guess. They thought the center of our own Milky Way galaxy might also hold a supermassive black hole. Just a few years later, on February 13th and 15th of 1974, astronomers Bruce Ballack and Robert Brown found something exciting. Using a special radio telescope in Green Bank, they found a strange radio source at the center of the Milky Way. It gave off a type of energy called synchrotron radiation, and it did not seem to move. Because of its strong gravity, they realized this could be the first real clue that a supermassive black hole, later named Sagittarius A, was hiding at the heart of our galaxy. Things took a big step forward in 1990, when the Hubble Space Telescope was sent into space. This powerful telescope let astronomers look at the centers of galaxies with much more detail than ever before. In 1994, one of its tools, called the Faint Object Spectrograph, looked at Messier 87 again. This time it showed that gas near the center was spinning very fast, about 500 kilometers per second, around a very small area. The only answer was a mass of nearly 2.5 billion suns packed into an area smaller than 1/4 of an arcsecond across. This was some of the strongest proof yet for a supermassive black hole. In 1995, a team led by Miyoshi used another powerful tool called the Very Long Baseline Array to look at Messier 106. They studied radio waves from water molecules, called an H2O maser, and found that the signal came from a disk of gas spinning around a compact object with the mass of about 36 million suns. The space was so small, just over 1/10 of a parsec across, that a group of smaller black holes could not possibly fit without crashing into each other. So again, the only real answer was a single, supermassive black hole. Another big finding around the same time was made in the galaxy MCG-6-30-15. Scientists found a special kind of X-ray signal called the iron K-alpha line. This signal was stretched out and bent in a way that showed it came from very close to a black hole, just 3 to 10 times the black hole's event horizon. This proved how extremely powerful and strange these objects really are. Then, on April 10th of the year 2019, something historic happened. The Event Horizon Telescope team released the very first picture of a black hole. It showed the huge black hole at the center of the galaxy Messier 87, giving the world a look at what was once only an idea. A year later, in March of 2020, scientists suggested that more rings of light might be found around that image, known as photon rings, which could help us learn even more about these mysterious giants. Even today, the question of where these supermassive black holes first came from is still being studied. Scientists know they grow by pulling in gas, dust, and even other black holes, but how the very first ones, called seeds, formed is still not fully clear. Some ideas suggest that they might have started from black holes that were just a few dozen or a few hundred times the mass of the Sun, created by exploding stars. Over time, these could have grown larger by feeding on surrounding material. Others think these seeds might have formed in a different way. In the early universe, before stars even existed, giant clouds of gas might have collapsed straight into something called a quasistar, which then collapsed into a black hole about 20 times the mass of the Sun. Or maybe dark matter helped pull in huge amounts of gas, forming supermassive stars that were tens of thousands of times heavier than the Sun, which then collapsed into black holes. There is even a newer idea suggesting that right after the universe began, giant stars, each with a mass of about 100,000 suns, collapsed into black holes, becoming the seeds of the monsters we see today. Some rare ideas go even further, suggesting that the universe did not begin with the Big Bang at all, but with something called the Big Bounce. If that were true, then maybe some supermassive black holes are older than the universe we live in now, having existed even before the last cosmic cycle ended. In the very early universe, huge clouds of gas floated around, far away in both space and time. These clouds were made of pure, untouched hydrogen and helium, what scientists call metal-free gas. When these clouds were hit by strong light known as Lyman-Ferner radiation, something strange happened. Instead of cooling down and breaking apart into smaller clumps, which usually leads to star formation, they stayed together. This was because the light stopped them from cooling, and gravity pulled everything inward, causing the whole cloud to collapse into a single, massive object. As this object collapsed, the pressure and thickness in the center became extremely high, about 10 million grams in every cubic centimeter. That is unimaginably thick. At this point, the object could no longer hold itself together. It did not become a star or even a quasi-star, a short-lived star-like object. Instead, it collapsed straight into a black hole. These massive objects are called direct collapse black holes, and they usually weigh about 100,000 times more than our Sun. In the year 2022, a computer model gave us more clues about how the very first supermassive black holes may have formed. According to this model, rare, chaotic clouds of gas, called primordial halos, were fed by unusually strong streams of cold gas. These cold streams kept new stars from forming too early, which allowed gravity to keep building up pressure. At last, gravity won, and the cloud collapsed into not just one, but two massive black holes. These two black holes had masses of 31,000 and 40,000 times that of the Sun. This showed scientists that the making of early supermassive black holes might have come from the normal processes of galaxy formation in the young universe. But there is another idea too: primordial black holes. These might have been made just moments after the Big Bang itself. If true, these black holes would have had much more time than other types to grow by pulling in matter. This could explain how some black holes reach supermassive sizes so early. Meanwhile, we already know that many black holes were born from the deaths of the first stars, and scientists have strong proof to support this. The other ideas mentioned above are mostly based on computer models and sums. To create a supermassive black hole, you need a small space packed with an enormous amount of matter that is not spinning too fast. Usually, matter in space has a lot of spin, or what scientists call angular momentum, and it takes time for this spin to be pushed outward during the process of accretion, when gas and dust fall into a black hole. This spinning motion is actually one of the biggest things slowing down black hole growth. Accretion is not only the fastest, but also the most visible way that black holes gain weight. In fact, most of a supermassive black hole's growth happens during times when it is swallowing gas very quickly. These dramatic events are what we see as quasars or active galactic centers, which shine brightly from the centers of galaxies. When scientists look far into space, and therefore far back in time, they see that quasars were much more common when the universe was young. This means that many supermassive black holes had already formed and were growing very early in the universe's story. Some extremely bright quasars have been found that existed when the universe was less than 1 billion years old. This tells us that supermassive black holes had already reached billions of times the mass of the Sun by that time, meaning they began forming in the first large galaxies. But there is a limit to how big a black hole can grow. According to today's ideas, the biggest possible weight for a black hole growing in the usual way, by swallowing gas, is around 50 billion solar masses. Beyond this point, the surrounding gas disk becomes unstable. Instead of feeding the black hole, the gas starts turning into stars that orbit it. The slowdown in growth starts when a black hole reaches about 10 billion solar masses, and past that, it becomes much harder for it to grow. However, in the most extreme cases, scientists think it might be possible for a black hole to grow as large as 270 billion times the mass of the Sun. For this to happen, the black hole would need to be spinning at nearly its fastest possible speed. Even then, the true upper limit of spin is just a little below the perfect maximum. Near this maximum mass, something unusual happens. The inner part of the disk around the black hole, the innermost stable orbit, becomes larger than the area where the black hole's own pull of gravity is strongest. When this happens, the disk can no longer form in the right way, and the black hole cannot keep growing by pulling in matter anymore. Also, reaching such extreme sizes is very unlikely. To grow that large, a black hole would need to keep spinning in the same direction as the material falling into it. But in reality, matter in space often falls in from random directions. This randomness, called chaotic feeding, means black holes often get pushed in both directions, sometimes spinning faster, sometimes slowing down. Over long periods of time, these changes usually slow a black hole's spin more than speed it up. Black holes also grow by joining together with other black holes, but these mergers usually lower the total spin as well. Altogether, these effects make it very rare for a black hole to grow larger than about 50 billion times the weight of the Sun, especially if it is not spinning very quickly. Only in very unusual cosmic situations do black holes even get close to that size, even though today's ultramassive black holes, often called UMBHs, found in quasars and at the hearts of galaxies cannot grow larger than about 5 to 27 times 10 billion suns, at least not by feeding on their disks of falling matter, and especially not within the current age of the universe. Some scientists think these cosmic giants could still keep growing far into the future. In fact, in the very distant future, during the slow collapse of huge groups of galaxies called superclusters, some of these black holes might reach almost unimaginably large sizes, up to 100 trillion suns. These giant black holes are very important in the universe. The strong pull of gravity at the center of many galaxies, where supermassive black holes live, is thought to be the driving power behind some of the brightest and most powerful objects we know, such as Seyfert galaxies and quasars. Interestingly, the mass of a black hole in the center of a galaxy often matches the size and weight of the galaxy itself, but this link changes depending on the type of galaxy. There is even a special connection, called the M-sigma relation, that links the weight of a black hole to how quickly the stars in the central bulge of the galaxy are moving. Faster star speeds usually mean a heavier black hole. When scientists mention an AGN, or active galactic nucleus, they're talking about the bright center of a galaxy where a supermassive black hole is actively pulling in matter. This process gives off huge amounts of light, making the center shine very brightly. Our own Milky Way's center, however, is not bright enough to be called an AGN. To explain the many different kinds of AGNs, astronomers created a unified model. This model says that the differences we see mainly come from a few important things, like how bright the AGN is and the angle from which we are viewing the material around the black hole. There are two main kinds of AGNs. One shines mainly through a thick disk of matter swirling into the black hole, while the other shoots out strong jets of energy moving almost as fast as light, blasting out from the poles of the black hole. When two galaxies, each with its own supermassive black hole, crash together and join, the black holes do not simply stay apart. Because of something called dynamical friction, the black holes slowly drift toward the middle of the new galaxy. In time, they get close enough, less than 1,000 parsecs apart, to form a pair. As they keep pulling on the stars and gas around them, they spiral closer and closer together, becoming a tightly bound binary pair with a gap of just 10 parsecs or less. If they get within 1,000th of a parsec of each other, the energy released as gravitational waves will finally make them join into a single, heavier black hole. After this powerful crash, the galaxy formed from the merger will already have settled down, and any early bursts of star-making or AGN activity will have faded away. But the black hole merger leaves behind something else, a powerful blast of gravitational waves. These waves can give the new black hole a strong kick, pushing it through space at thousands of kilometers per second. In some cases, the kick is strong enough to throw the black hole completely out of the galaxy. This unusual event is called a gravitational recoil. There is another way a black hole can be thrown out of a galaxy. Imagine two galaxies merging and forming a pair of black holes. Then a third galaxy joins, adding yet another black hole to the middle. When three black holes interact, things get messy. Usually the lightest one is flung out into space, while the other two shoot off in the opposite direction as a new binary pair. This kind of three-body gravitational dance is called the slingshot recoil. Any of the three black holes can end up being thrown out, and those that are sent flying into space are called runaway black holes. Astronomers have found several clues that may point to such runaway black holes. For example, if a bright AGN or quasar is not in the centre of a galaxy where we would expect it, that could be a sign. Or, if we see two different light signals coming from a single quasar, it might mean that a black hole is being thrown away. Some possible examples of thrown-out black holes are in galaxies like NGC 3718, SDSS 1133, 3C186, E1821 plus 643, and SDS-SJ 0927 plus 2943. Possible runaway black holes may include HE 0450-2958, CID42, and objects near the small galaxy RCP28. Runaway black holes can leave behind a line of new star birth as they move. In fact, a straight row of newborn stars near RCP28 was once thought to be the trail left by a runaway black hole. But later studies suggested that this feature might simply be a small galaxy seen from the side without a central bulge. And there is a fascinating process called Hawking radiation, named after the well-known scientist Stephen Hawking. According to quantum theory, black holes are not fully black. They slowly give off tiny amounts of heat energy because of strange effects near their edges, called event horizons. This process slowly makes the black hole shrink, and if left long enough, it would eventually vanish completely. For example, if there were a black hole 100 billion times heavier than the Sun, it would take about 2.1 times 10 to the power of 100 years to disappear. And if we imagine an even larger black hole, one formed during the collapse of a supercluster in the far future, with a weight of 100 trillion suns, it could take about 2.1 times 10 to the power of 1009 years to fully disappear. Some of the strongest clues that black holes really exist come from something called the Doppler effect. This is the same effect that makes a siren sound different as it moves past you. In space, it changes light. When matter is moving away from us, its light shifts to red, a process called red shifting. When matter is moving toward us, the light shifts to blue, or blue shifting. Near a black hole, things get very extreme. Matter orbiting close to a black hole has to move incredibly fast, almost as fast as light itself. Because of this, the part moving away from us looks much dimmer, while the part moving toward us looks much brighter. This makes something that is really evenly shaped, like a ring or disk of matter, look uneven and bent out of shape to our eyes. Modern computer-made pictures of black holes include this effect. One well-known example shows what the black hole at the centre of our own Milky Way galaxy might look like. This black hole is called Sagittarius A star, and it is based on a scientific model that many experts believe is very accurate. But our telescopes today are still not sharp enough to see this level of detail directly, so we depend on computer simulations for now. Still, scientists have been able to watch something else, matter swirling farther out from what we think are black holes. This matter moves much slower than light, which makes it easier to study. For example, water molecules in space can give off very specific radio signals called masers, which are like lasers, but with microwaves instead of visible light. By studying these masers in nearby galaxies, scientists have seen very fast Keplerian motion, meaning the matter moves in the way predicted by Kepler's laws of motion. This only happens when a huge amount of mass is squeezed into a very tiny space, something only black holes, or objects about to become black holes, can explain. For galaxies that are farther away, astronomers can study the width of certain light patterns, called broad spectral lines, which give clues about gas moving near the black hole's event horizon, the point of no return. One advanced method, called reverberation mapping, looks at how these light patterns change over time to estimate both the black hole's weight and, possibly, how fast it is spinning. There is strong proof that our own Milky Way galaxy has a supermassive black hole at its centre, about 26,000 light-years from the solar system. This region is called Sagittarius A star. Scientists have studied a star named S2, which travels in a stretched oval path around this strange object. It takes about 15 years and 2 months for S2 to make one full trip, and it gets as close as 17 light hours, about 120 times the distance between the Earth and the Sun, to the middle of the black hole. From the path of S2, scientists have guessed that the central object must weigh about 4 million times as much as the Sun, yet it must fit into a space no wider than 17 light hours, otherwise S2 would crash into it. Another star, S14, has shown that this strange object is even smaller, with a radius of less than 6 1/4 light hours, about the same as Uranus's path around the Sun. No other known object in the universe, except a black hole, could be this heavy and packed into such a small space. Even more amazing are the infrared views of glowing bursts coming from Sagittarius A star. These show a kind of superheated plasma, hot charged gas, moving incredibly fast, about 30% of the speed of light, in tight circles just outside the black hole's point of no return. These glowing spots seem to come from an overheated hot spot on the disk of matter falling into the black hole. This hotspot appears to follow a round path inside a strong magnetic field. On January 5, 2015, NASA saw an X-ray flare from Sagittarius A star that was 400 times brighter than normal, a record-breaking event. Scientists think this might have been caused either by an asteroid being ripped apart as it fell into the black hole, or by magnetic fields twisting and snapping inside the swirling gas. So far, we have clear proof of supermassive black holes in only a few galaxies. These include our Milky Way, the Andromeda Galaxy, also called M31, a smaller nearby galaxy called M32, and a few others outside our local group, like NGC 4395. In these galaxies, the speeds of stars or gas near the middle rise sharply as you get closer, which matches what you would expect if a massive object, a black hole, was pulling them in. In most other galaxies we have seen, these speeds do not rise the same way, so we cannot be sure if a black hole is there or not. Still, most astronomers think that almost every galaxy has a supermassive black hole at its centre. This idea comes from something called the M-sigma relation. In simple words, this means there is a strong link between the size of a galaxy's central black hole and how fast the stars in the galaxy's bulge move around. This pattern has been seen in about 10 galaxies, where we have very exact measurements, and it suggests that galaxies and their black holes might grow and change together. On March 28, 2011, astronomers saw something amazing: a supermassive black hole tearing a middle-sized star apart. They saw a sudden burst of X-rays and other signals, and the only explanation that fits is that a star got too close and was torn apart by the black hole's pull of gravity. This happened in a galaxy where the central black hole had been quiet until then. Based on what was seen, scientists think the black hole had a mass of about 1 million times that of the Sun. The event also created strong jets of material shooting out at high speeds, almost as fast as light, something called a relativistic outflow. A large part of the star probably fell into the black hole, and future views will help confirm this idea by studying how the light fades over time. The Andromeda Galaxy, which is about 2.5 million light-years from Earth, has a central black hole about 140 million times the mass of the Sun, much bigger than the one in the Milky Way. An even bigger black hole exists in the giant galaxy Messier 87, about 48 million light-years away. This black hole is about 6.5 billion times the mass of the Sun. The largest known black hole in our local area is found in the NGC 4889 galaxy in the Coma Berenices constellation. It is about 336 million light-years from Earth and has a black hole with a mass guessed to be 21 billion times the mass of the Sun. When it comes to quasars, extremely bright and far-off objects powered by black holes, we use indirect ways to guess their black hole masses. These ways are tricky and have a lot of uncertainty. One extreme example is the quasar TON 618, which might have a black hole with a mass of about 40.7 billion times the mass of the Sun. Its light comes from a time when the universe was still young, with a redshift of 2.219. Other quasars with big black holes include APM 08279 plus 5255, with about 10 billion times the mass of the Sun, and SMSS-J 2157 28.21 minus 360215.1, with about 34 billion times the mass of the Sun, almost 10,000 times bigger than the Milky Way's central black hole. Some galaxies seem to have two supermassive black holes at their centres, making a pair. If these black holes were to crash together, the event would make powerful gravitational waves. This kind of pair of supermassive black holes is thought to be a common result of galaxies joining together. One well-known example is the pair in the galaxy OJ 287, which is about 3.5 billion light-years away. This pair has the biggest black hole ever found in such a system, with a mass guessed to be 18 billion times the mass of the Sun. In 2011, a supermassive black hole was found in the small galaxy Hennies 210, which does not have a bulge. The exact meaning of this find for how black holes form is still unclear, but it might mean that black holes could have formed before the bulges in galaxies. In 2012, astronomers made another surprising find when they found a black hole in the galaxy NGC 1277, which is about 220 million light-years away in the Perseus constellation. This black hole was said to have a very big mass of about 17 billion times the mass of the Sun. This mass is about 59% of the mass of the galaxy's bulge, which makes up 14% of the galaxy's total star mass. However, other research suggested a different result. The black hole might not be that big, with a mass between 2 billion and 5 billion times the mass of the Sun, with 5 billion being the most likely. On February 28, 2013, astronomers used the NuSTAR satellite to measure the spin of a supermassive black hole for the first time. The black hole they studied was in the galaxy NGC 1365, and they found that its event horizon was spinning almost as fast as the speed of the light. In September 2014, data from many X-ray telescopes showed that the very small, dense, and ultra-compact galaxy M60UCD1 has a black hole at its centre with a mass of 20 million times the mass of the Sun. This black hole makes up more than 10% of the total mass of the galaxy. This find was surprising because this black hole is 5 times bigger than the one at the centre of our Milky Way galaxy, even though M60UCD1 is less than 5,000ths the mass of the Milky Way. Some galaxies do not have supermassive black holes at their centres. While most galaxies without a supermassive black hole are small dwarf galaxies, one case is still puzzling. The supergiant elliptical galaxy A2261 BCG, which is one of the biggest known galaxies, has not been found to have an active supermassive black hole with a mass of at least 10 billion times the mass of the Sun, even though it is more than 6 times the size and 1,000 times the mass of the Milky Way. However, several studies have said that the possible black hole at its centre could have a mass anywhere between 6 billion and 10 billion times the mass of the Sun. This means the galaxy might either have a black hole that is not actively growing, or one that is smaller than 10 billion times the mass of the Sun. In December 2017, astronomers reported the find of the farthest quasar ever seen at that time, Euless J 1342 + 0928, which has the farthest supermassive black hole, with a redshift of 7.54. This beat the earlier record held by the quasar Euless J 1120 + 0641, which had a redshift of 7. In February 2020, astronomers said they had found an eruption in the Ophiuchus supercluster, which was the most powerful event ever seen in the universe since the Big Bang. This event happened in the Ophiuchus cluster in the galaxy Neve 1, where nearly 270 million times the mass of the Sun's material was being pulled into its central supermassive black hole, which has a mass of 7 billion times the mass of the Sun. The eruption lasted about 100 million years and gave off 5 million times more energy than the most powerful gamma-ray burst ever seen. The eruption made shock waves and jets of high-energy particles that spread into the space around it, making a huge cavity about 1.5 million light-years wide, which is 10 times the width of the Milky Way. In February 2021, a team of astronomers made an amazing announcement. They had made one of the most detailed pictures of the universe ever seen, a picture that showed the spots of about 25,000 active supermassive black holes. These are not just normal black holes, but the giant ones at the hearts of galaxies, each one millions or even billions of times heavier than our Sun. What made this picture so special was not just the number of black holes it showed, but the way it was made. It covered about 4% of the northern part of the sky, called the Northern Celestial Hemisphere. That may sound small, but in the endless size of space it is still a huge area full of cosmic wonders. To uncover these hidden giants of the cosmos, astronomers turned to an extraordinary tool known as the Low Frequency Array. often called LOFAR for short. Think of it as a gigantic ear stretched across Europe, made up of thousands of antennas and radio dishes spread over several different countries. But unlike our eyes, which see the universe in light, LOFAR listens to the universe. It does not pick up sound we can hear. Instead, it detects incredibly low-frequency radio waves, signals far below the range of the human ear. These ghostly waves travel across unimaginable distances, carrying the faint whispers of cosmic events. They are especially good at revealing the fierce, high-speed jets and bursts of raw energy that blast out from black holes as they greedily swallow surrounding matter. With LOFAR, scientists can map these otherwise invisible outbursts, turning the universe's silent drama into something we can finally observe. A direct collapse black hole is like taking a cosmic shortcut to creating something enormous. Instead of waiting for a star to be born, live its life, and then die in a violent collapse, these monsters skip all the middle steps. They form when a giant cloud of untouched ancient gas, made mostly of hydrogen and helium, gives into gravity and falls straight into a black hole. No star stage, no explosions, just a direct plunge into darkness. These are not ordinary baby black holes. They are what scientists call black hole seeds, the very first building blocks that later grow into the colossal, supermassive black holes we find at the hearts of galaxies. Astronomers believe that these giants appeared when the universe itself was still very young, between about 100 million and 250 million years after the Big Bang. That period, in scientific language, is linked to what is called a redshift between 15 and 30. Unlike smaller black hole seeds that were born from the very first generation of stars called population 3 stars, direct collapse black holes came into existence because of a runaway effect, predicted by Einstein's theory of gravity, known as a general relativistic instability. When they were born, they were already huge. Most had masses of about 100,000 suns, though some range from 10,000 up to 1,000,000 suns. The whole idea of direct collapse black holes was introduced as an answer to a puzzling cosmic riddle. Astronomers had found supermassive black holes existing less than 1 billion years after the Big Bang, yet it seemed almost impossible for such giants to grow so fast from tiny stellar black holes. But for a direct collapse black hole to form, the universe had to provide some very rare and very special conditions. Pure gas. The cloud had to be free of metals. In astronomy, anything heavier than helium is called a metal. If there were heavier elements, the gas would cool too quickly and break into stars. Atomic cooling gas. The gas had to be cool enough to clump together, but not so cool that it fragmented into many little stars. A flood of ultraviolet light. Specifically, Lyman-Werner light, which destroys hydrogen molecules, some of the best coolants in space. Without those molecules, the gas could not cool enough to split apart into stars. When all these things lined up perfectly, the gas cloud could not shatter into stars. Instead, it collapsed as one enormous hole under its own gravity. The center reached a density of around 10 million grams in every cubic centimeter, and burned with a temperature close to 10 billion degrees. At that point, relativity itself said the cloud could no longer hold together. It collapsed into a black hole, often with the weight of 100,000 suns, and in extreme cases up to 1 million suns. Because they skipped the star stage entirely, astronomers gave them their fitting name, direct collapse black holes. If the gas cloud had even a tiny bit of heavier elements, more than 100,000th the sun's metal content, then it would cool differently. Instead of collapsing as one, it would fragment into stars. In those cases, some stars at the center of these regions could grow into supermassive stars by greedily feeding on nearby gas, a process scientists poetically call supercompetitive accretion. In July of the year 2022, computer models revealed something surprising. There might be another way to make black hole seeds. A rare gas halo, fed by cold streams of material rushing in, could prevent stars from forming without needing ultraviolet light or special cooling. In these simulations, when the halo reached about 40 million suns in mass, at a redshift of 25.7, gravity finally overcame the turbulence inside. The result was the birth of two gigantic stars, which later died and collapsed into black holes weighing about 31,000 and 40,000 suns. Even so, direct collapse black holes are thought to be extraordinarily rare. Some models suggest that at a redshift of 15, there might be only one such black hole in a cube of space a gigaparsec across. To put that in perspective, a gigaparsec is more than 3 billion light-years. Yet in the most optimistic scenarios, their numbers could reach up to 10 million in that same volume of space. In the year 2023, another study suggested that at a redshift of about 10, dark matter halos weighing between 1 billion and 10 billion suns could each host multiple direct collapse black holes. Over time, these halos would merge together, helping to create even larger black holes in the growing universe. Earlier research, looking further back in time to redshifts above 13, painted an even more fascinating picture. It suggested that there was once a golden age for the birth of direct collapse black holes. Around a redshift of 14, they may have formed in abundance, creating a kind of cosmic chain reaction. Once one formed, it made it easier for others nearby to appear. This flurry of black hole births slowed down by a redshift of 13, but the seeds planted in that era would later grow and merge into the massive black holes we see in galaxies today. One of the most important milestones in this story came in the year 2016. A team led by Harvard astrophysicist Fabio Pacucci used data from the Hubble Space Telescope and the Chandra X-ray Observatory to find the first two candidates for direct collapse black holes. These mysterious objects, seen at redshifts greater than 6, shone unusually brightly in infrared light compared to other sources in the early universe. Just what scientists expected from such black holes. Astronomers now hope that the James Webb Space Telescope will uncover more evidence and perhaps confirm these cosmic seeds. While primordial black holes may have formed in the very first heartbeat of the universe, in the earliest fractions of a second after the Big Bang, direct collapse black holes were later titans, born hundreds of millions of years afterward. They stand as proof that in the young universe, there was more than one path to creating a cosmic giant. Black holes come in many shapes and sizes, and one of the most mysterious kinds is known as the intermediate mass black hole, often called an IMBH. These strange objects sit right in the middle range. They are not small, but they are not the universe's giants either. Their mass stretches from about 100 times the weight of our Sun, all the way up to 100,000 suns. That is far heavier than the black holes made when massive stars collapse at the end of their lives. Those are called stellar black holes. But they are still tiny compared to the true giants of the cosmos, the supermassive black holes, which sit at the centers of galaxies and can weigh more than 1 billion suns. For a long time, scientists wondered if these medium-sized black holes were real or just an idea. Over the years, a handful of possible examples have appeared, both inside our own galaxy, the Milky Way, and in other galaxies close by. But astronomers did not actually see these black holes with their eyes. Instead, they searched for clues. They studied how clouds of gas moved under a strong pull that suggested something very massive was nearby, or they watched the bright glow of the accretion disk, a swirling ring of blazing hot gas and dust that forms when a black hole hungrily pulls in matter. These hints convinced scientists that IMBHs might be hiding in those places. One of the most thrilling pieces of evidence for IMBHs came not from light but from ripples in the very fabric of space and time. On the 21st day of May in the year 2019, at exactly 3 minutes and 2 seconds past 3 in the morning Coordinated Universal Time, detectors picked up a powerful gravitational wave signal. The event was given the name GW 1905-21. These space-time ripples came from a titanic collision between two black holes, one with a mass about 85 times that of our Sun, and the other about 65 suns. Their crash forged a brand new black hole weighing 142 suns. The leftover mass, about 8 suns, was blasted out as pure energy in the form of gravitational waves. This incredible discovery was officially shared with the world on the 2nd of September 2020, marking the first confirmed detection of an intermediate mass black hole born before our very instruments. Before that groundbreaking event, the best hints of IMBHs came from faintly glowing galaxies called low-luminosity active galactic nuclei. These galaxies are dim, but their unusual light suggested something powerful was stirring inside them. By using a clever technique known as reverberation mapping, measuring how gas near the black hole reflects bursts of light, astronomers could even estimate the size of the hidden monster. A striking example lies in the spiral galaxy NGC 4395, about 4 million parsecs away. At its heart sits a suspected black hole with a mass of around 360,000 suns. A much larger search came from a project called the Sloan Digital Sky Survey. After carefully studying about 1 million galaxy-light readings, scientists uncovered a treasure trove of 305 possible IMBHs. Out of this group, 10 were spotted giving off X-rays, which strongly hinted that they really were black holes of medium size. Other intriguing candidates come from ultra-luminous X-ray sources, or ULXs. These are dazzlingly bright points in the X-ray sky, often found in galaxies where new stars are being born. A famous example lies in the starburst galaxy M82. ULX often appear near young star clusters, leading scientists to believe they could be black holes devouring nearby stars. To prove this beyond doubt, astronomers must carefully measure how the companion star moves and how its light shifts under the pull of the black hole. Another hunting ground for IMBHs is within globular clusters. These are ancient spherical swarms of stars that orbit galaxies like the Milky Way. Scientists watch how stars at the center of such clusters move, hoping to catch the telltale tug of something massive. But so far the evidence has been shaky. One cluster, known as M31G1, was once thought to host an IMBH. At first, the data looked promising, but later studies showed that the same results could be explained without needing a black hole at all. Gravitational waves may yet solve this puzzle. If an IMBH merges with another black hole, or with a dense object such as a neutron star, their spiraling dance would shake the universe and send ripples racing across space. Instruments like LIGO and Virgo could catch these signals, giving us clearer proof of these elusive black holes. There is also a helpful rule of thumb called the M-sigma relation. It links the weight of a black hole to the movement of stars near the center of its galaxy. According to this rule, smaller galaxies with fainter cores should host black holes weighing somewhere between 10,000 and 1 million suns. The lightest black hole ever suggested by this method lies in a galaxy named RGG 118, with a mass of about 50,000 suns. In November of the year 2004, astronomers made headlines when they announced the possible discovery of the very first IMBH in our Milky Way. This black hole, called GC-IRS 13e, was estimated to weigh around 1,300 suns. It sits just 3 light-years away from the Milky Way's central giant, Sagittarius A. GC-IRS 13e is part of a cluster of 7 stars, thought to be the remains of a much larger cluster that was shredded apart by the powerful gravity near the galaxy's core. This finding gave strength to the idea that supermassive black holes may have grown by slowly swallowing up smaller black holes and star clusters. But science is never settled so easily. In the following year, 2005, a team of German astronomers challenged the claim. By studying how the stars in that cluster moved, they argued that there might not be a black hole there after all. If an intermediate mass black hole really does lurk near the center of our galaxy, scientists believe it may yet reveal itself through the subtle changes it causes in the orbits of nearby stars. In the month of January in the year 2006, a group of scientists led by Philip Carrot from the University of Iowa made a claim that stirred excitement in the world of astronomy. They reported that they had detected a repeating signal, something called a quasi-periodic oscillation, coming from what might be a black hole in the galaxy known as Messier 82. This possible black hole, given the name Messier 82X1, appeared to be feeding on a nearby red giant star, which was slowly shedding the outer layers of its body. The discovery was made using NASA's Rossi X-ray Timing Explorer, a special satellite built to study these mysterious high-energy signals from space. But even this exciting find came with doubt. The repeating signal only lasted for about 4 cycles, which might not be enough to prove that it was a true pattern. Some experts thought it might just be random noise in the background of space, and even if the signal was real, its cause was still unclear. Was it the motion of the star as it orbited, or some slower process happening deep inside the black hole's swirling accretion disk? Only 3 years later, in the year 2009, another breakthrough came when astronomer Sean Farrell and his team spotted something unusual. They discovered a strange object called HLX-1, which turned out to be an intermediate mass black hole. What made HLX-1 so fascinating was that it seemed to be surrounded by a tiny cluster of stars, almost like a miniature galaxy tagging along with it. The host galaxy, named ESO 24349, appeared to have collided long ago with a smaller galaxy that carried HLX-1. While most of the smaller galaxy's stars had been swallowed into the larger one, the black hole remained behind, a lonely survivor of a cosmic crash. In the year 2012, on the 9th day of July, scientists in Australia using a powerful radio telescope operated by CSIRO made another bold claim. They believed they had found the first clear evidence of an intermediate mass black hole, supported by strong signals in radio waves. Only 3 years later, in 2015, researchers at Keio University in Japan stumbled upon yet another mystery. They were studying a peculiar gas cloud named CO0.400.22 and saw that the gas inside was moving at wildly different speeds. After running computer models, they suggested that the best explanation was a black hole weighing around 100,000 times the mass of our Sun. Yet doubts lingered. Later studies proposed that the strange gas movement could instead be caused by shock waves from exploding stars known as supernovae. The puzzle remained unsolved. Then, in the year 2017, scientists thought they had uncovered another hidden black hole, this time inside a globular cluster, a dense ball of stars called 47 Tucanae, found in the southern sky. The suspected object was not like the ordinary black holes born from dying stars. Instead, it seemed to belong to the rare middle-sized class, possibly a few thousand times heavier than our Sun. The clue came from watching pulsars, special stars that spin and flash beams of radiation like cosmic lighthouses. Their motions hinted that something massive was pulling on them. But when further studies were done, the evidence for a black hole faded, leaving the case uncertain. By the year 2018, the astronomers of Keio University were back in the spotlight with another intriguing discovery. Near the very centre of our Milky Way galaxy, they found streams of cold gas orbiting something unseen. This hidden object, with the technical name HCN 0.0090.044, was estimated to have a mass of about 32,000 suns. If confirmed, it would be the third known black hole in the mysterious Middle Range, too heavy to be born from a single star, yet far too light to qualify as a supermassive black hole. Just 1 year later, in 2019, a dramatic cosmic event brought new clues. Astronomers detected gravitational waves, ripples in the very fabric of space and time, caused by the collision of two black holes. One had a mass about 66 times greater than the Sun, and the other was about 85 times the Sun's mass. When they merged, they created a new black hole about 142 times as heavy as the Sun. During the crash, an incredible amount of energy equal to about 9 suns was released in the form of gravitational waves. This cosmic explosion, known as GW 190521, gave scientists another piece of evidence for the existence of medium-sized black holes. The search continued in the year 2020, when astronomers identified yet another possible candidate. This one, with the long name 3XMMJ 215022.4 055108, was spotted in the direction of the Aquarius constellation, about 740 million light-years away from Earth. It too could be an intermediate mass black hole. Then, in 2021, came another stunning report. A black hole weighing about 100,000 times the Sun's mass appeared to be hiding inside a globular cluster called B023G78, located in the Andromeda Galaxy. Though this result was first shared as a preprint, it quickly caught the attention of astronomers around the globe. By the year 2023, attention shifted to Messier 4, the closest globular cluster to our planet. Astronomers noticed that the stars inside it were moving in unusual ways, as if something very heavy and invisible was at its heart. The hidden object seemed to weigh about 800 suns, and its dense, compact nature made scientists suspect it might be a black hole. Yet another possibility was that it was a crowded gathering of smaller remnants, like white dwarfs, neutron stars, or tiny black holes clumped together. The very next year, on the 10th of July in 2024, another striking study grabbed headlines. 7 stars in the famous cluster Omega Centauri were seen racing around as if pulled by something huge and unseen. The scientists estimated the mysterious object's mass to be at least 8,200 suns, making it another strong candidate for an intermediate mass black hole. All these discoveries, scattered across the years, have made one thing clear. intermediate mass black holes remain one of the universe's most puzzling mysteries. They do not seem to follow the usual paths of formation. They are far too massive to come from the death of a single star, the way smaller black holes form, yet they are not nearly massive enough to be the giants known as supermassive black holes, which dominate the centres of galaxies. So how do these middle-sized black holes come into existence? Astronomers have several ideas. One possibility is that smaller black holes, over millions or even billions of years, slowly merge together until they form a larger one. Another idea is that in crowded star clusters, huge stars might crash into one another, creating a supersized star that eventually collapses into an intermediate black hole. A more exotic thought is that some of these black holes might have formed not in recent cosmic history, but at the very dawn of time, shortly after the Big Bang, making them primordial black holes. There is also the intriguing question of whether a single gigantic star could collapse straight into an intermediate black hole. For this to happen, the star would need to be extremely massive, at least 260 times heavier than our Sun. Some scientists believe this could occur if several stars in a dense young cluster merged into one colossal star, which then collapsed under its own gravity. Yet such events would be extremely rare and hard to observe directly, leaving these mysterious black holes among the universe's most closely guarded secrets. A rotating black hole is not just an ordinary black hole, it is a special kind that spins around an invisible axis of its own, much like a child's toy top that never stops twirling on a table. This endless turning is more than just motion. It gives the black hole something scientists call angular momentum. That is a fancy way of saying it has both speed and a particular style of spinning that defines how it moves through space. Spinning is not a rare trick in nature. It is almost a universal rule. The tiniest particles, such as electrons, have spin. Our planet Earth twirls once every single day. The Sun rotates on its own schedule. Galaxies swirl like giant whirlpools of stars, and black holes born from violent stellar deaths and cosmic collisions naturally inherit the spin of the matter that made them. Physicists who use Albert Einstein's grand theory of general relativity discovered 4 neat mathematical descriptions for black holes. 2 of these describe the spinning ones, the Kerr black hole and its cousin, the Kerr-Newman black hole. According to a famous principle called the no-hair theorem, every black hole, no matter how it was made, can be described in the end by just 3 features: its mass, its spin, and its electric charge. Nothing else matters. The details of what star collapsed to make it, or how exactly it was formed, are lost forever inside the event horizon, the invisible boundary that seals the black hole from the outside world. No information from within this dark boundary can ever escape to the universe beyond. Because most stars are spinning when they collapse, the black holes they leave behind usually spin too. But stars and planets are rarely strongly charged, and if a black hole ever gained an electric charge, it would quickly pull in nearby particles of the opposite type, cancelling it out. This is why the black holes we find in reality are expected to be nearly neutral in charge, but still spinning at incredible speeds. For this reason, when scientists talk about real black holes in the universe, they almost always mean Kerr black holes, rotating giants with little or no charge. These whirling titans can be born in more than one way. The most common path is the collapse of a massive star that was already spinning before its death. Another route is through cosmic pileups, when compact objects like stars, clouds of gas, or stellar remains crash together and merge, carrying some of their spin into the newborn black hole. Since nearly everything in the universe rotates, astronomers believe that almost every black hole is in truth a spinning one. In the final months of the year 2006, astronomers revealed something astonishing in the Astrophysical Journal. They had measured the spin of a black hole in our Milky Way galaxy, one with the technical name GRS 1915 plus 105. To their amazement, it seemed to be spinning at a staggering rate of about 1,150 times every single second, almost at the fastest speed nature allows a black hole to turn. When a rotating star collapses into a black hole, the collapse can also unleash one of the most powerful outbursts in the cosmos, a gamma-ray burst. These are violent beams of high-energy light that can blaze across billions of light-years, reaching Earth as a fleeting but dazzling flash from the farthest depths of the universe. Even more incredible is that rotating black holes can give away some of their energy. Through a strange process known as the Penrose process, part of their spin can be tapped and converted into usable energy. This happens in a bizarre zone just outside the event horizon called the ergosphere, where space itself is dragged around at almost the speed of light. Over unimaginably long stretches of time, a spinning black hole could slowly lose its rotation, eventually becoming a Schwarzschild black hole, one with no spin at all. But in practice, black holes are thought never to fully stop spinning. The mathematical descriptions of Kerr and Kerr-Newman black holes, born from Einstein's legendary field equations of the year 1915, remain some of the finest tools we have for understanding these cosmic whirlpools. They describe not what lies inside, but the strange behavior of space and light outside the event horizon. Near a spinning black hole, space itself is so twisted that even light cannot travel in straight lines. Light can orbit around the black hole, looping several times before escaping. This creates a magical effect. If a black hole lies between us and a distant galaxy, the galaxy's light can appear distorted, stretched, or even multiplied, like a cosmic hall of mirrors shaped by gravity itself. In the year 2021, researchers managed to work out a complete mathematical picture of how light bends and curves around the spinning middle of a Kerr black hole. Then, in the year 2022, mathematicians confirmed something remarkable. The solution that Roy Kerr discovered back in the year 1963 was not only correct, but also stable. This meant that the spinning black holes Einstein's equations predicted more than a century earlier could exist in reality, and that they would remain steady over time. Rotating black holes even seem to have moods, shifting between heating and cooling states. When they release energy, whether through the Penrose process or other mechanisms, they give up some of their spin and grow hotter. When they stop shedding energy, they gradually cool. This mysterious cycle adds yet another layer of wonder to these spinning monsters of the cosmos, turning them into both destroyers and givers of energy in the grand drama of the universe. A binary black hole, sometimes called a black hole pair, is a cosmic system made up of two black holes locked in a tight orbit around each other. Just like single black holes, these pairs come in different sizes. Some are stellar mass binary black holes, which are born either from huge pairs of stars that both collapse into black holes, or from chance meetings where two lone black holes become trapped by each other's pull of gravity. Others are supermassive binary black holes, which scientists believe are formed when two galaxies crash together, bringing their giant central black holes into the same gravitational dance. For a long time, proving that binary black holes really existed was a huge challenge. Black holes by their nature hide from direct view, and until recently the tools we had for finding them were limited. But scientists knew that if two black holes were to spiral together and finally merge, the event would unleash a mind-blowing amount of energy, not as light, but as ripples in the very fabric of space and time itself, called gravitational waves. These waves have unique patterns, or fingerprints, that can be predicted using Albert Einstein's theory of general relativity. By the late 20th century and early 21st century, binary black holes became a focus of intense study because they offered one of the best chances to prove that gravitational waves were real. Such mergers are among the most powerful known sources of gravitational waves in the universe. As the two black holes orbit each other, they give off these waves, slowly losing orbital energy. This makes their orbits shrink, a process called inspiral, until they finally crash together. Once merged, the new single black hole goes through a stage called ring-down, in which any uneven shape is smoothed out, and the remaining energy is released as more gravitational waves. In the last tiny fraction of a second before merging, the black holes can reach unbelievable speeds, and the gravitational wave signal reaches its peak. The existence of stellar mass binary black holes and gravitational waves themselves was finally proven in September of the year 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal known as GW150914. This signal came from two black holes, each weighing about 30 times the mass of our Sun, spiraling together about 1,300,000,000 light-years away. In their final 20,000ths of a second, the pair released an amount of energy equal to about 3 suns, peaking at a staggering 3.6 times 10 to the power of 49 watts, more power than all the stars in the observable universe put together, could produce at once. Supermassive binary black holes are harder to confirm. Astronomers have found strong candidates such as galaxies that appear to have double cores, signs of two black holes still far apart after a galactic crash. One striking example is the galaxy NGC 6240. Other cases include galaxies that seem to have a single core but give off double emission lines, such as SDSS J 1048007.74 plus 0, 05543.5, and EGSD 2 J14 2033.665 25917.5. Some galaxies, like OJ 287, produce flares on a regular schedule, hinting at a huge object moving in orbit around a central black hole. In the galaxy J0437 plus 2456, measurements suggest that the central supermassive black hole is moving in a strange way, perhaps because it is part of a binary system, or because two galaxies are in the middle of merging. The quasar PKS 1302-102 seems to hold a binary black hole with an orbital period of about 1,900 days. When two galaxies collide, their central supermassive black holes are unlikely to smash head-on. Instead, they usually swing past each other unless something, most often dynamical friction, slows them down. Dynamical friction happens when a black hole's gravity slingshots nearby stars, speeding the stars up while slowing the black hole. This steals energy from the black holes, allowing them to become a bound pair. As more energy is drained, their orbits shrink until they are only a few parsecs apart. But here lies the final parsec problem. As the black holes get closer, they clear away the matter in their path, and without more matter to interact with, they may not merge within the age of the universe. Gravitational waves could finish the job, but only when the black holes are much closer together, less than 1/100th of a parsec apart. Some observations, such as in PKS 1302-102, suggest that pairs have indeed reached this stage. To solve the final parsec problem, astronomers have suggested several ideas. One is that fresh matter, gas or stars, might drift in close enough to interact with the pair and steal away more orbital energy. If enough stars pass nearby, they can be thrown out at high speeds, pulling the black holes together. Dark matter might also help, but it would need to be the kind that interacts with itself, or else it too would be thrown away before the merger. One of the most dramatic solutions involves a third supermassive black hole entering the system during another galactic collision. In such a case, one black hole might be kicked out, but often the three will engage in chaotic gravitational interactions. These wild orbits can make the black holes pass through larger regions filled with matter, losing energy more quickly, or stretch their orbits into very long shapes, which lets gravitational waves carry away energy much more effectively when the black holes are at their closest approach. The life of a pair of black holes locked together in a cosmic dance begins with what astronomers call the inspiral stage. This is when the two black holes move around each other in an orbit that slowly but surely shrinks over time. At first, this shrinking happens very slowly, because the gravitational waves they release, ripples in the very fabric of space and time, are extremely weak when the black holes are still far apart. Imagine two dancers circling each other in a huge ballroom. Their steps are slow and wide at the beginning, but gravitational waves are not the only reason the orbit shrinks. The black holes can also lose a bit of their spinning motion, known as angular momentum, through encounters with other matter in the area, like wandering stars or gas clouds. As the black holes drift closer, their speed begins to rise dramatically. The faster they move, the stronger the gravitational waves become, which makes their orbit shrink even faster. Once they are close enough, the shrinking turns into a rapid collapse of their orbital dance. There comes a point called the innermost stable circular orbit, or ISCO for short, which is the very last fully stable orbit they can have before everything changes. After this, the black holes plunge toward each other in a final unstoppable spiral and then collide in a merger. At this moment, the gravitational waves they produce reach their most powerful peak. Right after the merger, the newborn black hole is anything but calm. It is twisted, stretched, and far from balanced. It begins a process called the ring down, where it sends out gravitational waves in a pattern that is strikingly similar to the fading sound of a bell after being struck. Scientists call these fading patterns damped oscillations, or quasi-normal modes. As the ring-down continues, the waves quickly weaken, showing that the black hole is becoming more stable and perfectly symmetrical. Studying this part of the signal is crucial because it helps confirm that the final object is indeed a Kerr black hole, exactly as Einstein's general theory of relativity predicts. The very first time humans detected such an event was on the 14th of September, the year 2015, at 9 hours and 50 minutes Coordinated Universal Time. Using the highly sensitive LIGO detector, scientists observed two black holes, one about 36 times heavier than our Sun and the other about 29 times heavier, as they whirled together and merged into a single black hole weighing roughly 62 suns. In the final heartbeat of this cosmic dance, about 3 suns worth of mass was turned into pure gravitational energy, reaching a staggering peak power equal to 200 suns per second, around 50 times greater than the combined light and energy of every star in the observable universe. This extraordinary event happened about 440 million parsecs away from Earth, which is between 600 million and 1.8 billion years in the past, and remarkably, the signal matched exactly what scientists had predicted using advanced computer models of Einstein's equations. When scientists try to understand and predict the gravitational waves from these events, they use different mathematical methods for different stages of the black hole dance. For the inspiral stage, when the black holes are still far apart, they can use post-Newtonian approximations, a clever way of adding small corrections to the simpler equations of Newton's gravity. These calculations can be second order, 2.5 order, or third order. Another method, called the effective one-body approximation, turns the complex two-body problem into something that can be solved as if it were just one object moving in a curved space. For the ring-down stage, scientists use black hole perturbation theory to study how the distorted black hole vibrates and settles down. But to capture the full story, the spiral, merger and ring-down, they must solve Einstein's general relativity equations in their entirety. This requires numerical relativity, a branch of science where supercomputers create detailed models of space and time and how it changes during the event. These simulations are incredibly tricky, because they need to focus very closely on the region near the black holes, while also covering a wide enough area to track the gravitational waves as they travel out to infinity. To make this possible, scientists use special coordinate systems, like Boyer-Lindquist coordinates or fisheye coordinates, which allow them to keep detail where it matters most. Although attempts at numerical relativity began in the 1960s and 1970s, it was not until the year 2005 that 3 separate research groups independently cracked the code, developing new techniques that finally allowed long-term simulations of orbiting black holes through all stages of their evolution. One well-known effort, called the Lazarus Project, stitched together results from different models at the moment of merger to create a full picture. From these calculations, scientists can even figure out the binding energy of the black holes, the amount of energy holding their orbit together. As the system reaches the innermost stable orbit, the binding energy reaches a turning point before plunging into the final collapse. Gravitational waves from these events can also have interesting tails, formed when the waves scatter in the strong gravitational zone near the black holes during the late inspiral. And in the final ring-down stage, a spinning Kerr black hole produces waves linked to its rotation, a phenomenon called frame dragging